Utastorl, which I see here. You need to unmute your.
Okay,
Yes.
fine. I'm looking forward to my presentation later. Nice to meet you.
All right, next on the list, Steven Klabe from Ilmiano, Germany. I don't see him. Philip Fant from Munich. I don't see him either. Parimarjan Neji from MIT. Well, these figures are discussing later, much later, I guess. Maybe they haven't joined yet. And the last one, Zahra Sandri from Oklahoma. Okay, we'll have time to do that right before each session anyways. And I just saw that the other general co-chair has just joined. May, would you like to say hello to everyone?
Hello, everyone. I don't know who else is from the West Coast.
Here, yeah.
Oh,
Also
hi.
West Coast, yeah.
Early in the morning.
Morning, yeah. Just 6:30.
Excellent company for the morning coffee.
Yeah.
So everything seems to be okay. And by the way, are we supposed to use Slack for questions? No?
Well, ICD is, but we're smaller. I'm thinking that the Zoom group chat would probably be sufficient.
Okay.
Yeah.
I was going to say the same thing. ICD suggested that, but I think we can use the Zoom chat for these questions and interaction.
Yeah, okay, so, sounds great.
Well, I guess while we're waiting, I can give some general instructions mainly about Zoom. I'd like to ask the audience to keep yourselves on mute, throughout the different presentations. We'll have time during the Q&A after each talk for discussing the paper. In addition, if you have any questions during a talk, you could always use the chat feature. There's a chat. You should see a chat icon somewhere in the bottom. So if you think of a question while someone is talking, you can go ahead, type that in, and then we can get back to it at the end of each presentation. And then finally, it's good to keep your view in speaker mode once we start, so you can see the person who is speaking and the presentation rather than the gallery mode. Yeah, so for now, we'll just wait for a little bit longer for more people to join. Thank you.
It's so beautiful to see all of us across multiple time zones being here and excited. And I just saw Herodotus drinking frappe, which seems that there the temperatures reach the 30 degrees Celsius, as opposed to here in Pittsburgh, where we still wearing coats and the temperature is 5 degrees Celsius.
No, it's not 30 yet, but it's around 27, 28. So it's getting there. Give it another week or so.
But coffee is frappe. It's cold
Yes.
coffee.
Yes, it is.
Oh, question concerning getting the audience to switch over to HardDB's Zoom. So, so after the opening, we will tell people to switch over to the other Zoom. And when people do come onto this Zoom, will they be able to know that they should switch?
The answer is yes. Basically, once Herodotus complete his opening presentation, he will invite us to switch to the other channel. And in June, when he completes his session sharing of the invited speaker, he will invite us to switch back to the SMDB side. Similarly, Shimin is going to do the same for the afternoon keynote speaker.
But so if somebody missed the start and then they come in 5 minutes later, they're going to go to the web page and click on the SMDB Zoom.
If they, yeah, we have announced it, and also on the website.
Okay.
We put the links where they should join, and I hope that everything works well.
I will
we
also
won't have too much confusion.
Okay.
Yeah, I'll talk about that as well, and I will write it on the Zoom group chat with the link so that everyone knows.
Yes.
When
Yeah.
to click.
Okay. Yeah. That will take care of it. Yeah.
Yeah, actually, I'm not sure whether we need to put a link on our webpage or Twitter or some other social media. Because for the as we discussed, where if people talk up, let's say join 5 minutes later, then probably they cannot find the link.
Well, we can put a slide up and say, please go to HardDB's link for our Zoom.
Yeah, maybe. Yeah.
Good. Yeah, that's good. I can do that.
It's like, yeah, it's like put it on the screen of that room.
Yeah.
Okay. Yeah, it's good.
Yeah, but how should we invite people to join back from Feifei's talk to Guoyang's talk?
No, Guolink's talk will be in within the HardDB active workshop. In order to minimize context switch, we decided to do that.
I mean, how to join back after his talk?
Oh, we're going to click back to our go back to the program and click into that link again.
Yeah.
So when you click now, if everybody clicks to go to the other session, they will say, do you want to leave this session and join the other one? You confirm, and then you are joining the other session. The only headache is going to be for 34, whatever we are numbered now, 35 people being waiting in the waiting room to be admitted. But we coordinated with, I believe, Brian, our wonderful student helpers with Viva, to be aware of this switch and help us out.
And Viva is our student volunteer?
Yeah, Viva is the volunteer here.
Okay, thank you, Viva.
Hello, everyone.
Hello.
I'll be in contact with Brian to ensure that the switch will be seamless. So there should not be any problem with that regard.
Excellent. Thank you again.
Sure, no worries.
By the way, there is a question about sharing slides in Zoom charts. Personally, I'm not familiar with Zoom charts. If anyone has any insight, let us know.
The only way that I think you can do so is to provide a link to where you have posted the slides.
Yeah, actually, I think well, after Gordon's talk, I can hear those the Asper just to put a link, right? I think that's much easier for other audience to join to join back to SMDB, right?
Yeah, that's a very good question. If speakers have their slide decks available and provide with the URL, then we can quickly post them also in the program as well on the website as well as on the chat. So yeah. That's June said that we can, the audio people can follow it.
I've also just shared my my screen with the slides. Can you guys see it?
Yes, we do.
Thank you. Okay, I think it's almost time. I guess we can just wait another minute or so, and then we can start. Panos, you just give us the go ahead, and we can start.
Yeah, my intention was to wait until we become 50, but I am happily to say that we crossed the 50 mark. We are 51 at this point, and I guess maybe it's time to start so that we don't delay our switch to the keynote speech and invited talk. Again, my name is Panos Chrysanthis. I'm at the University of Pittsburgh, and it's my great pleasure to welcome you all to say good morning or good evening, depending on your location. And it's to say that it's exciting that we have this opportunity to run the self-managing database system, even though that we are going through terrible times. So, but at least I'm happy to see everyone being around healthy and safe. And at this point, I will turn the microphone to Herodotus to do the introductions and with respect to the rest of the team. Maybe I should have done it, but I will allow Herodotus to do it and not to further delay the opening. Again, welcome.
Thank you, Panos. Well, it is also my great pleasure to welcome everyone at the 11th International Workshop on Self-Managing Database Systems, sponsored by the IEEE Data Engineering Workgroup on Self-Managing Database Systems. My name is Herodotus Herodotou from the Cyprus University of Technology. I'm one of the two program chairs, along with Yingjun Wu from Amazon Web Services. Panos Chrysanthis from University of Pittsburgh and Mei-Shun Xu from Oracle are the general chairs of the workshop, while Konstantinos Costa, also from the University of Pittsburgh, offered his valuable assistance as the vice program chair. Well, the notion of self-managing or self-adaptive databases has been around for over 40 years now, and it has sort of become the holy grail of the database community that wishes to make, aspires to make the systems to be self-configuring, self-optimizing, self-healing, and self-protecting. Now, of course, the emergence and the popularity of cloud computing has increased the stake of automation in database manageability, especially as service providers must now configure and manage thousands of nodes. There are a lot of decisions that need to be made. Some decisions will affect the performance of the system, such as which indices to use, what kind of formatting and compression to use. Other decisions will affect the availability of the system, such as which backup and replication strategy to use. Security, of course, is of paramount importance nowadays, right? So we have to rethink about auditing and encryption mechanisms and so on. While, of course, provisioning is of high importance. When do we introduce new nodes into a running system? How do we upgrade or patch existing systems, and so on? Hence, one of the main challenges is the need to scale, this type of self-managing capabilities to the level of thousands of nodes, while of course taking economic factors into account. Hence, it is crucial to rethink and design database system components with self-adaptivity in mind from the beginning, right? For example, it's necessary to have some building ability for tracing or collecting statistics within the different components, as well as have mechanisms for enacting policies across the different components. Now, the collected data can then be used with some data mining, machine learning, or artificial intelligence in order to make various predictions, how the workload will behave, how the system will behave under different loads, and then use those to make further decisions about how to control the system, what kind of policies to use, and so on. So the aim of the SMDB workshop is to present and discuss ideas related to all of these challenges and, of course, potential solutions towards the development of truly autonomous database and data processing systems. Now, this year's workshop features 6 research papers out of a total of 9 that we had, organized in 2 sessions. Now, perhaps it's the first time ever that the sessions were actually organized based on geographic location in order to accommodate our speakers. Of course, the first research session consists of 4 papers from Europe, covering topics from relational databases, NoSQL databases, stream processing systems, while the second research session comes from 2 papers from the US covering some core topics in self-managing databases such as cardinality estimation and online index selection. It is with great pleasure to also say that we have 2 excellent keynotes and 1 invited talk organized for this year's workshop. The first keynote is from Fei Li, Vice President of Alibaba Group, who is going to talk to us about software hardware co-design for cloud-native databases. The second keynote is by Sandesh Rao, Vice President of Oracle Autonomous Database Group, who will discuss AIOps with the Oracle Autonomous Databases. We also have 1 invited talk by Guoliang Li from Tsinghua University, who's going to present an AI native database they've been building. Now, all of these 3 talks are actually joined with HardBD and Active workshop, which is running concurrently to the SMDB workshop. So the first keynote and the invited talk will start in a few minutes at the HardBD and Active meeting room, while the second keynote, which will take place in a few hours, will be here in this meeting room. Now, after the 2 research sessions and the invited talks, at the end, we're also having a panel chaired by Panos Chrysanthis, where we will be discussing the future of the data engineering workgroup on SMDB. Last but not least, I would like to extend my sincere gratitude to our esteemed program committee, all these people who reviewed the papers and made sure we have an excellent program for this year's workshop. So once again, thank you all for joining SMDB 2020. And unless I guess there are any comments or remarks, I'm going to ask you to exit this meeting and join the HardBD and Active meeting. I have placed the link on the chat in order to hear the first keynote and the first invited talk. And afterwards, switch back to this meeting to continue on with the rest of the SMDB program. Thank you once again.
I guess there are no more questions. So let me also invite everybody to switch to our keynote speaker session and invite the talk. See you on the other channel.
Mm-hmm. Hi, everyone. Let's give 1 or 2 minutes for everyone to switch rooms, and then we're going to get started. Unfortunately, we won't have much time to take a break. I don't want to make sure that we stay on schedule so that we don't have any issues with the timing of the next keynote that's going to take place after this session. So we'll start in a couple of minutes. All right, let's make sure that our speakers are here, at least the first couple of them. Theodoros Toliopoulos, are you here? Say hi.
Hello.
Perfect.
Hi.
Hello, Yuta.
Hi, I'm here.
Perfect. Steven Klabe.
Hi, I'm also here.
Perfect. And Philip Fent.
Hi, I'm here.
Great. So all 4 speakers are here. That's wonderful. Panos, you're on mute. It seems like you're saying something.
No, I would say just wait for 1 more minute.
Yes, I will.
Yeah, I just saw Zhangqing's question on starting the conference. I think Costa just made an announcement that it would be in another couple of minutes.
All right, everyone. I think we can get started. Welcome back to the first research session of SMDB. Please note that we're recording this session and will be made available afterwards. This session will run for about 80 minutes, consist of 4 talks. Each talk will get about 20 minutes, 15 minutes for the video, and 5 minutes for Q&A. Keep yourself muted. If you have any questions, please add them to the chat and we'll discuss them at the Q&A. All right, so our first talk for the day is titled Adaptive Distributed Partitioning in Apache Flink by Theodoros Stoliopoulos, a PhD student from Aristotle University of Thessaloniki in Greece. Theodore, you'd like to make a brief introduction before we start the presentation?
Hello, everybody. Just as Herodotus said, I am a PhD student in Aristotle University, and we have been working on this project for some time now. That's all, Herodotus. Thank you.
Thank you. Viva, can you play the first video, please?
Greetings, everybody. I hope you are all healthy and well. My name is Theodoros Stoliopoulos. I am a PhD student in Aristotle University of Thessaloniki, and I will be presenting you our work on adaptive distributed partitioning in Apache Flink. Starting off with our motivation. We have been working for a long time on distributed real-time outlier detection on intense data streams. More specifically, we have been working with distance-based algorithms where a data point is an outlier if it has less than k neighbors in a range R around it. 2 data points are neighbors if the distance between them is less than R. Of course, in a streaming environment, we also have the notion of windows. So we need to assess the outlierness or inlierness of its data point on every window slide with regard to the incoming and expiring data points. As a result, we also need to hold a state for each window in order to store the already computed metadata of alive data points. In previous works, our goal was to transfer the state-of-the-art algorithms, centralized algorithms, to a distributed setting using Flink, as well as create some novel algorithms. One of the problems we encountered was the partitioning of data points. We wanted to have independent processing tasks, meaning that each task should run the outlier detection algorithm locally and output its local outliers without the need to communicate with the other tasks. The solution we found was to partition incoming data points based on their value into non-overlapping cells. Each of these cells, which represent a key space, is assigned to a distinct task and outlier detection algorithm. Due to the nature of the detection algorithms, we need to have some data replication in order to output the complete and correct outliers. As an example, in the image of this slide, the red data point belongs to cell number 1, and of course it is transferred to that cell. But it is also replicated and transferred to cells number 3 and 4 since it is within range R of their borders. The only job of the replicas is to provide information on possible neighbors and not be outputted as an inlier or outlier. In order to do this, we used 2 ways of splitting the data space into cells. The first one is based on a grid such as the image, and is used for the Euclidean space only. This way is the fastest of the 2. The second way is based on a vantage point tree and supports any metric space. The reason why we used both of these types was because the first one, which is more common for real values, is faster, but only supports Euclidean space. Meanwhile, we wanted to also have all metric spaces. The problem we encountered with this type of partitioning is the load imbalance. The distribution of real-world data streams continuously changes, and as a result, some of the tasks might end up with more data points than the others. In extreme cases, one task might take most of the data points of the ingestion. This, of course, creates a big overhead on the whole system and slows down the whole process. The solution that we present in this work solves this problem by letting the partitioning tasks decide on the fly if the cell boundaries need to change. The decision is taken from the computation of a cost function based on metadata from the outlier detection tasks. This can only be done by transferring the metadata from the processing task backwards into the partitioning tasks. When we use the word adaptive, we distinguish it into two categories. The first one is more common and widely studied for many years and involves the repartitioning of keys. This category is used mainly in the context of adaptive query processing. The second one, which fits perfectly into our problem and is studied in this work, is the change on the key space and the keys boundaries, which helps when the data distribution changes. The final bit of background information is about Apache Flink. Flink is an open source distributed stream processing engine widely used for real-time analytics. Its job represents a direct acyclic graph with each operator being a vertex and the data flows being the edges. Due to the DAG, data flows from a forward operator to a previous one is prohibited. On the physical layer, each operator is split into distinct tasks without intercommunication that are assigned to different machines in a cluster. The initial architecture of our framework is captured in this slide. The data source transfers the incoming data to the partitioning tasks, and when the partitioning process ends, each data point is assigned to a cell. It is further processed by the outlier detection algorithm. Finally, the local outliers are outputted for further processing. In order to solve the load balancing problem, we need to add a feedback loop to the architecture that will move metadata from the processing tasks backwards into the partitioning tasks. Of course, this cannot be completely done in Flink exclusively. That is why we decided to use an external system to support this feedback loop. More specifically, we use the main memory data structure called Redis, which is also widely used. Redis is used as a fast input and output cache that will temporarily store the metadata needed for the cost function. In order to connect Redis to the jobs operators, we need two more tasks for Flink. The first one is a salt output task. It is the right red circle that writes the metadata of each outlier detection task to Redis on every window slide. The second one continuously reads the data from Redis and transfers them to the partitioning tasks. Due to synchronization issues, the broadcast operator has only one task, which means that only this single task reads the metadata from Redis and moves them into all of the partitioning tasks. The final part of the solution is an addition to the partitioning operator. Its first function that already existed beforehand is the key assignment, which partitions each new data point to a specific cell. The addition this time is the second function that acts as a controller one and decides whether to change a cell's boundaries or not based on the cost function. The cost function is computed from the read metadata from Redis, and since each task runs independently, the controller needs to be deterministic and produce the same results for each task. The resulting architecture of our solution looks something like this, where the solid lines are the initial architecture and the dashed lines are the additions. Now, going to the algorithmic part of the controller function, we need to impose some restrictions in order to tackle synchronization and state integrity problems. When the function decides to change the cell's boundaries, it creates 3 distinct time periods. The first one is called buffer period, and it delays the border change in order to synchronize all partitioning tasks. The second one is called transient period, and starts when the boundaries change. During this time, both the old and the new boundaries are stored and used when necessary. This period is essential for state integrity in order to produce the complete and correct result of outliers. Unfortunately, due to time reasons, details about the exact policies that ensure the correctness of the results can be found in the paper. The final period is called stabilization, and it is used in order for the states of each processing task to return back to normal. During this period, a new change cannot occur, and any metadata read from Redis is discarded. This image on this slide depicts the controller function with its distinct steps. The 4 last lines are the buffer period, the key change, and the transient and stabilization period. One thing of attention here is the boundary change line, and more specifically, the alpha parameter. Alpha is a small number that controls the amount by which the boundaries will change, and this is a variable. Next, going from the more theoretical and technical stuff to the practical ones. Here we have the experiments comparing the adaptive setting to the static setting, which is the red line for both techniques. The 3 different lines above the red line are the 3 different adaptive settings using 3 alpha variables. The left plot indicates the average replicated points, and the right one indicates the average processing time of the slowest task. In all settings, the static is slower with more replicas than the respective adaptations, while there is no clear winner for the alpha parameter. The decrease of processing time means that the load of each task is better balanced, while the decrease of the replicas, of the number of replicas, indicates that the change of the boundaries create better distinguished cells. All of these experiments were completed using a real-world dataset called stock with 1 dimension. Comparing the 2 techniques, it seems that the grid technique is always faster than the tree one, as expected. In order to distinguish the times that the algorithm adapts in comparison to the dataset's distributions, we present the following plots. The x-axis is the time period during which the data ingestion was taking place. The left y-axis represents the values of the data points, while the right y-axis represents the maximum data points that the key had when the decision to change its boundaries was taken. Finally, in the plots, the crosses and the red axis represent the timestamp that the decision to adapt was taken for each technique. The left plot shows the real-world dataset called stock. Since the distribution continuously changes, the algorithm tries to adapt as the marks show during the whole ingestion. In order for the decision-making to be more clear, we also use the synthetic dataset by combining 2 Gaussians back-to-back. As expected, the adaptations start after the big change in distribution and continue during the ingestion until it fully adapts. The time it takes to adapt is quite big since each time only 1 key changes. Comparing the 2 techniques show that for both of them, the cell creation and changing are similar since the decisions to change a key are close to each other. The final dataset we used is also a synthetic one, and it is created by combining 10 Gaussians concurrently. As the distribution is the same during the dataset's ingestion, the decision to adapt is correctly never taken. To close up, our work uses an external main memory cache called Redis to create a feedback loop on Flink's operators. This loop helps make the partitioning tasks adaptive and self-load balancing by using a cost function based on the metadata from the forward processing tasks that are transferred through Redis into the backward partitioning tasks. In other words, in summary, we have devised a technique that adaptively partitions data points in Flink in scenarios where the grouping depends on value ranges and the boundaries of these ranges are user-defined. Although our motivation is continuous distance-based outlier detection, any technique in which the data grouping depends on partially overlapping cells can benefit from our solution. For example, another case study is spatio-temporal queries. Moreover, our solution is novel also in the sense that it shows how we can render Flink adaptive through designing and implementing a feedback loop. Our next steps are to incorporate the new architecture in our distributed outlier detection engine, which is an open source project. We also want to experiment more with assessment policies, with new assessment policies and cost functions by using different metadata produced by the processing tasks. Finally, we will try to find new and more eager repartitioning techniques, such as concurrently changing more than one key, which is the case at this point in time. Thank you very much for your time. I will gladly answer any questions you have. Stay safe.
All right. I haven't seen any questions related to the talk pop up. As for the recorded videos, to be honest, we don't know. The ICD conference hasn't announced that to us yet. As soon as we know, we'll of course notify everyone. Now, does anyone have any questions for Theodoros? Well, if not, I actually have a question. Good work, first of all. It's very interesting. My question is about the alpha parameter. Based on my understanding, it sort of represents the magnitude of change in the partitioning space, and based on the results, it seems like it can have a positive or a negative effect, which of course means that there are different trade-offs involved when setting the alpha parameter. Can you briefly discuss the trade-offs that are involved in these decisions, and whether there are any insights on how someone would set it to get the optimal results?
Yes, of course, Herodotus. First of all, the alpha parameter depends. We want it to be a small number so that the borders will not change that much. But it also depends on the dataset used and the dimensionality. In our experiments, we used one dimension, so changing a border was quite easy. That's why on our experiments, we used 1, 2, and 3 different values. The difference between each change was not really that big. As you've seen in the slide, if you remember it, only on the tree-based technique, the one alpha value was a little slower than the others. But the winner was not clear, just as I said, because sometimes the smaller alpha parameter wins, sometimes a bigger alpha parameter wins. We want to experiment more on this. We haven't really tried many different alpha variations, and we want to experiment more on this and see how much it is affected by the dataset and each use case separately.
Great, thank you. One more question. How exactly do you use Redis?
Okay, so in order to transfer the metadata we need from the processing tasks backwards into the partitioning tasks, we need something to save them, to store them for a little while. Mm-hmm. On every window, the processing tasks output their metadata and store them temporarily into Redis. And so Redis is used as a fast read-write cache, main memory cache, so that the partitioning task, the broadcasting task, to be more specific, reads the metadata from Redis, and then updates the cost function.
Great. And one last question, I guess we have 1 more minute. So Flink, as most stream processing engines, are designed to work with multiple source inputs, which push data in the query network. The design you propose suggests a centralized decision module. Can you share if you have worked on any decentralized decision-making architectures? And if yes, can you please elaborate?
I'm not really sure I understand this question, but this is not centralized. We use Redis only as a centralized system, but Flink can be deployed into a cluster of computers. So each partitioning task is independent from the others. So let's say we have 3 computers, we can have 20 different partitioning tasks. Each one will be working separately from the others. The main problem with our implementation in the broadcast function was to take the input from Redis and distribute it into the partitioning functions. And that's why we use the broadcasting operator. So one task reads from Redis and transfer the metadata to all partitioning operators that will independently and separately decide whether to change the adapt or not. If I answered your question.
All right, thank you. All right, I guess Panos is asking one more quick question. How much effort was it to integrate Flink with Redis?
The integration was not much, was not too difficult. The only thing we needed was the output. So how to write to Redis from Flink, which, if I remember correctly, has some already libraries, official libraries. And again, to make Redis our source, which also has, if I remember correctly, some code already implemented. So to connect them was pretty easy.
All right, well, great. That's good to know. All right. Well, thank you very much, Theodore.
Thank you too.
Let's move on to the second talk for today, towards self-adapting data migration in the context of schema evolution in NoSQL databases, by Jutta Stroll, who's a professor at Darmstadt University of Applied Sciences. Let me give the mic to her for a brief introduction.
Hello, thank you for the introduction. The work I will present is a joint work with the research group of University of Rostock and University of Passau and our research group. And I think we can start with the presentation.
Welcome to my talk towards self-adapting data migration in the context of schema evolution in NoSQL databases. The presented work were developed in a joint DFG project between Darmstadt University of Applied Sciences, University of Rostock, and University of Passau. After a short motivation, I will introduce into the challenges of big data migration. Afterwards, I will present our developed approaches for self-adaptive data migration, and finally give a conclusion and an outlook. The motivation of our works comes from Agile software development. Agile software development implies frequent schema changes. So schema-flexible NoSQL databases are very popular within Agile software development because we can store heterogeneous versions of the data in the NoSQL databases. But what about the variational data? How to migrate the variational data? When to migrate them and for which cost? State of the art are migration of data within the application code with error-prone and expensive data migration scripts. In the practice, schema evolution is one of the top 10 fears about the future of the DBMS field, as Michael Stonebringer explained in 2018. So our approach is to propose an optional schema management for NoSQL databases too. This schema management and schema evolution management contains of 2 tasks. The first task is the schema evolution management, and the second task is the data migration as a safe process based on schema evolution management. In this talk, we will focus on the data migration. Before discussing data migration, we need to make a brief excursion to NoSQL schema evolution operations. We proposed a schema evolution language for describing structural changes of the data. We distinguish between single-type operations and multi-type operations. Single-type operations like add, rename, delete refer to a single entity type, whereas multi-type operations like copy, move, and so on refer to more than one entity type. These multi-type operations are very important in the context of NoSQL databases because we need them for refactoring operations within Agile software development, as well as for denormalization operations, which are very common for performance reasons in NoSQL database application development. Data migration is performed based on these schema evolution operations. The challenge for data migration is to understand and estimate the impact of different data migration strategies. However, this is very important to choose the appropriate data migration strategy. Furthermore, we want to propose self-adapting data migration approaches. Approaches which initiate an appropriate migration strategy or adjust the parameters of a migration strategy. There are various data migration strategies with different impact on the migration costs and the latency overhead. Traditionally, data is migrated eagerly, which means that data is migrated when the schema changes. However, this strategy comes with a lot of migration costs, especially when the database is hosted in a cloud environment. So data may also migrate lazily, which means that data is not migrated when the schema evolution occurs, however, when the entity is loaded into the application. So of course, we minimize with lazy migration the migration costs. On the other hand, lazy migration adds a latency overhead to read and write operations. So the question is, how can we reach a compromise between these two competing goals of minimizing latency
Vimba, if you hear me, we have lost audio. Could you please take a look at it?
one entity type. These multi-type operations are very important in the context of NoSQL databases because we need them for of minimizing latency, the migration costs and the latency. This slide summarizes the characteristics of the different data migration strategies with respect to migration costs and latency overhead. Furthermore, we notice that for all data migration strategies except for eager migration, it's necessary to implement query rewriting within the NoSQL database or in a layer between the application and the database. The question how to choose the right data migration strategy is still open. The decision depends on the characteristics of the data set, the data access pattern, the frequency and characteristics of the schema evolution, of course, on the DBMS, the configuration of the DBMS or the database, like distribution, replication, and so on, and last but not least, on the cloud pricing model. As a first step, we implemented MigCast. MigCast is a tool on top of our schema management middleware Darwin, and based on the previously introduced input parameters like characteristic of data set, data access pattern, schema evolution, and DBMS and cloud pricing, MigCast simulates and calculates the migration costs and the data access latency. MigCast consists of a workload simulator, a cost calculator, and a latency profiler. The user may specify results are presented in 5 charts. The most important are the both on the left side, the cumulated migration. The results are presented in 5 charts. The most important are the both on the left side, the cumulated migration costs and the latency per entity access. And with help of these charts and the log results, you can see the differences of the various data migration strategies depending on your own application parameters. In the next step, we want to propose self-adapting data migration approaches. What is self-adapting data migration? That are techniques that automatically initiate an appropriate migration strategy or adjust the parameters of a migration strategy. The next question is, when is the self-adapting executed? The point in time of the adaptation depends on the requirement for the application in terms of the trade-off between latency and migration costs, typically specified in service level agreements. And these requirements are currently no longer met by the system, then it's the right point to adapt the strategy. Of course, this depends on the query workload, the number and kind of changes in the data model of the specific application. So how does self-adapting data migration works? In the paper, we propose different self-adapting data migration approaches. We distinguish between 2 use cases. The first use case with a random distribution of data accesses, and the second use case for localized distribution of data accesses, which is more common for database applications. For the first use case, we propose an approach where the frequency of the incremental migration is adapted. For the second use case, we propose 3 different approaches to adapt the parameters of the predictive migration. These 3 approaches I will present in the next minutes. The first one, we call it complexity adaptive approach. The motivation comes from the observation that the execution of a multi-type operation, like copy, move, split, merge, and so on, generates a significant amount of latency overhead. So it's very expensive in terms of latency if we access an entity which has to be migrated with a multi-type operation. And so the idea is to adapt the prediction set size for the predictive migration depending on the number of multi-type operations. So when we exceed a threshold for the number of multi-type operations, we increase the prediction set size to cover more entities. And after the subsequent migration, we decrease the prediction set size. This approach is already implemented in our Darwin and MigCast tools. And the figure shows an example. We call this approach adaptive strategy. And we can see that the latency for the adaptive strategy is lower than for the predictive approach without this adaptation. The next approach is called predictive requirement adaptive approach. The idea is to implement a feedback control system based on the SLA requirements regarding latency and migration costs. So we constantly monitor latency and migration costs. And if the current latency exceeds a threshold, we increase the prediction set size. Of course, this increase of the prediction size comes with more migration costs. So when we reach a sufficient latency and exceed the migration costs in a specific time frame, we decrease the prediction size. So we constantly adapt the prediction set size depending on the current values of latency and migration costs, and depending on the requirements of the SLA. The third approach considers the efficiency of latency change per migration investment, and is therefore called predictive efficiency adaptive approach. We use the difference of the latency as function. And the derivative of the latency function with respect to the prediction set size measures how the latency changes with respect to increasing or decreasing the prediction set size. If the latency exceeds latency threshold, we increase the prediction set size. And if the derivative of the latency function exceeds an efficiency measure, we decrease the prediction set size. This efficiency measure, mean, can be thought as a threshold value to meet the requirement regarding a minimal efficiency of migration costs. So to conclude my talk, I gave you an introduction into the challenges of big data migration and proposed several self-adaptive data migration approaches. In the next step, we want to evaluate these self-adaptive data migration approaches and develop further approaches. Furthermore, we currently develop a NoSQL schema evolution and data migration benchmark, and will further develop our data migration advisor. In the long run, it's an interesting challenge to evaluate these techniques in the context of multi-model databases and polystores. So thank you for your attention, and I'm looking forward to your questions.
All right, apologies for the spotty audio at a couple of points, but it seems like now it is fixed. There was one clarifying questions on the chat. You'd already answered, but in case some people are not following the chat, I'm going to repeat it. It's a clarification question. By NoSQL, are you referring to key value store, or is it a relational store?
Okay, we are referring to document stores as well as white column stores. And our system, we currently support MongoDB, Couchbase, and Cassandra, but the interface is very general, so we are able to support more systems in the form of document stores and white column stores.
Good. Well, the floor is open to any other questions you guys may have.
if you have questions later, then you can contact me later on, of course.
Mm-hmm. Excellent. Thank you, Yuda, for the interesting talk.
Thank
you. Let's move forward then to the third paper of the session, titled PatchIndex, Exploiting Approximate Constraints in Self-Managing Database by Steven Klabe from the University of Ilmenau, Germany. Steven, would you like to introduce yourself?
Yeah, it's basically all being said. Thank you. And I hope you enjoyed the presentation. My name is Steffen Klebe, and I'm happy to present you our paper, PatchIndex, Exploiting Approximate Constraints in Self-Managing Databases, which is a joint work with Kai-Uwe Sattler of the University of Ilmenau and Stefan Baumann from Actien, Germany. Automatic constraint discovery is an important part of self-managing databases. In modern big data applications, data can often be unclean, making it challenging for self-managing tools to discover constraints, if they even exist. There are different reasons for that. First, data may be integrated from different sources, leading to duplicate values or arbitrary insertion orders. As a result, schema heterogeneity and integrating tuples into a common schema may lead to missing values or null values. Second, real-world data may contain anomalies like duplicate names, shared telephone numbers, or shared addresses. Approximate constraints contain valuable information that can't be defined as a constraint, as some values violate the constraint definition. As a result, this information is lost. See the example here. It's not possible to declare the order ID column as unique, as the value 3 occurs 2 times, but it seems that it is nearly unique. Additionally, without actually sorting the table, the order date column is sorted except a single value. Not defining constraints in database systems may lead to poor query performance as a consequence. Typical real-world use cases further underline the need to handle these constraints. In many applications, users combine database systems with dashboard generation tools on top to simplify reporting or make use of the built-in query generators. While increasing the ease of use of database systems, these tools challenge the systems with complex query on the one hand, and on the other hand, they rely on metadata queries to generate elements in the dashboards, for example, drop-down menus. A query graph of a typical metadata query is shown on the right. Here, every branch is a count-distinct query. Additionally, many applications maintain time-based data, so for example, IoT applications where data come from sensor networks. In these datasets, columns can also be co-sorted with the time of tuple generation, like measurements, version numbers, or auto-increasing values. These two use cases would definitely benefit from information about the uniqueness or the order of the data. Handling approximate constraints has 3 major challenges. First, the constraints need to be discovered, of course. Second, we need to efficiently represent the information of the approximate constraints. And third, we need to find possibilities to then actually benefit from the information in, for example, query execution. With our paper, we provide 3 major contributions. First, we provide methods to discover the approximate constraints that can be easily integrated into existing self-managing tools, and we show how to handle them in our PatchIndex data structure. Second, we describe possibilities to exploit the information in query optimization and accelerate queries using approximate constraints for different use cases. Third, by carefully designing the way exceptions are handled, we enable systems to hold multiple sort keys in a single table, as we do not change the way data is physically stored. Our basic idea is to support the definition of approximate constraints, which are constraints that hold for most tuples except a potentially small number n of exceptions. In order to handle these exceptions, we introduced the generic PatchIndex data structure that is able to handle arbitrary constraints. Currently, we integrated uniqueness and sorting constraint. We compare 2 different design approaches for the index, which is the identifier-based approach, and the bitmap-based approach. And we integrate the index into query optimization. For the further discussions, we start with some intuitive definitions. The formal definitions can be found in the actual paper. First, we define a set of patches PC for a given column C, which basically just contains the row IDs of all exceptions to a given constraint. Then we can say a column C is a nearly unique column if we can find a set of patches such that after we exclude these rows, the column C is unique. Similarly, a column C is a nearly sorted column if we find a set of patches such that the column is sorted after excluding the rows of PC. An example can be seen in the figure below. The column C becomes unique if we exclude tuples 1, 2, 3, and 7. Please note that we need to exclude all occurrences of non-unique values, as we later want to perform subqueries separately on the exceptions and the remaining tuples, and need this condition to ensure correctness of the query result. The column C also becomes sorted if we exclude tuples 4 and 7. This choice is ambiguous, as excluding tuple 3 and 7 would also be a possible solution. The choice of a nearly unique column was not ambiguous, as we aim for the minimal set of patches to satisfy this constraint. Now discovering an approximate constraint translates to finding such a set of patches. For nearly unique column, we need to find all occurrences of non-unique values and assign their row IDs to the set of patches. This can be done using a hash table, but as this is also done by a distinct aggregation, we can use database operators to do this in a more generic way using a SQL query. In this query, we find all values that occur more than once using an aggregation and recover the row IDs by a self-join with the actual table. Here we need to pay special attention to null values, as they should be assigned to the set of patches. Therefore, the actual implementation uses an outer join and further conditions. As we said before, this result is unambiguously minimal set of patches. For nearly sorted columns, we utilize the longest sorted subsequence algorithm by Michael Fredman. As a prerequisite, the algorithm needs the full data. It then tracks the longest sorted subsequence iteratively in metadata arrays. As it performs a binary search for each element, the worst case runtime for the algorithm is O of n times log n. In order to construct the set of patches afterwards, we then invert the results with respect to the relation to get the tuples that are not included in the sorted subsequence. These tuples are assigned to the set of patches. As we have seen in the example before, this choice is ambiguous, but the described approach obviously computes a minimal set of patches. The main task for the actual index is then to manage these exceptions. We provided two basic approaches, which is a dense and a sparse approach. While the identifier-based approach stores the 64-bit row IDs of the exceptions, the bitmap-based approach stores a single bit for each row of the table, where a bit at position I indicates whether tuple I belongs to the set of patches. As the bitmap-based approach therefore has a constant memory consumption, it is expected to be the better choice in terms of memory consumption for exception rates larger than 1.5%. The index filling is realized using a post query to the actual index definition query, which is basically just performing the constraint discovery mechanisms that we described before. Due to this design, the index does not change the way data is physically stored, which enables the definition of multiple sort keys per table. To benefit from the PatchIndex, we introduced the PatchIndex scan. The main goal of the scan is to split data into two distinct groups to perform subqueries separately on them. After discussing various possibilities, we decided to realize this by introducing new selection operators exclude patches and use patches, which merge the PatchIndex information on the fly to the data flow. These selections are placed directly above the scan operator in the query execution tree and provide support for several common scan techniques like partitioning or scan ranges. With this, we are now able to jump into query optimization. Here, we present three major use cases to integrate patch indexes into query, namely distinct, join, and sort queries. In the queries, X and Y are arbitrary subqueries, which are currently not allowed to contain any joins or aggregations, so the optimization is applied to the lowest operator in the tree. Additionally, the black operators show the input query, while the blue ones are the operators introduced by the query optimization. For nearly unique columns, we can accelerate distinct queries by dropping the most expensive operator of the tree, which is the distinct aggregation, after we excluded patches. As we already noticed, these tuples are then unique. The aggregation is only performed on the set of patches, which should be significantly the smaller part of the tuples. Afterwards, the result of both subtrees are combined using a union operator. Here we can see why we need to have all occurrences of a non-unique value in the set of patches. If we would leave out one occurrence, the data would still be unique, but the value would occur in both subtrees and therefore occur twice in the combined result, which would then be not unique anymore. For nearly sorted columns, we can accelerate join and sort queries. For the join operator, we can replace the generic hash join with the cheaper merge join after we excluded the patches, as data is sorted then. The patches are joined with the other table using a hash join, and the results are again combined using a union operator. For the sort operator, we can follow a similar approach than for the distinct operator. The expensive sort operator can be dropped for the subtree that excluded the patches, as data is then ensured to be sorted. The sort operator is only performed on the set of patches, and both subtrees are combined using a merge operator to then preserve the order. To evaluate our solution, we integrated the concept into ActionVector, which is built on the X100 or vector-wise analytical query engine. We performed a set of microbenchmarks to evaluate the performance impact for varying exception rates. Therefore, we designed a custom data generator and generated datasets with 100 million tuples and different exception rates. For the uniqueness constraint, the exceptions form 100,000 groups, while exceptions for the sorting constraints were just chosen randomly. In the graphs below, we can see the performance impact of patch indexes for distinct and sort queries. For the distinct query first, we see that the reference runtime decreases with higher exception rates, as the number of unique values decreases and therefore also the number of aggregation groups. The runtime when using a patch index is significantly faster and increases slightly with increasing exception rates, as then more tuples need to pass the aggregation operator. Therefore, the overall speed up of course decreases, but using a patch index never impacts query performance in a negative way. For the sorting constraint, the reference runtime increases with higher exception rates, as the internal sort implementation performs better the more sorted the data already is. Again, we can observe a significant performance gain when using a patch index. Runtimes also increase with increasing exception rates, as more tuples need to be processed by the sort operator. Therefore, again, the speedup shrinks and becomes nearly zero for high exception rates. In order to show that use cases occur in datasets, we took basic examples of the TPC-DS benchmark. Here we can find a typical case, a fact table that is nearly time sorted. For scale factor 1000, joining this catalog sales table with the date dimension was accelerated from 1.4 to 0.7 seconds by the use of a patch index. For nearly unique columns, we choose the customer table as an example. A distinct query on the email address column, which has a quite small exception rate, can get a speedup of nearly 4. Additionally, we intentionally choose another column with a very high exception rate. Here we can also observe a small acceleration of the distinct query. Nevertheless, this should not be the typical use case of a patch index. In conclusion, we have seen that approximate constraints contain valuable information systems can benefit from that. We describe discovery methods for nearly unique and nearly sorted columns that can be integrated into database self-managing tools. Additionally, we have seen that queries can be accelerated in various use cases using patch indexes and our experiments show the impact on query performance even for high exception rates. Therefore, as it shows the impact for very high exception rates, the bitmap-based design approach is the chosen approach. Additionally, with patch indexes, tables can have multiple approximate sort keys, as it does not reorder the physical data. As the results were quite promising, we will further enhance the approach. The most important part is the update support, where we aim to avoid full index reconstruction and full table scans. Furthermore, we aim for a more comparable evaluation using common benchmarks. All right, so thank you very much for your attention, and I'm happy to answer some questions from you.
All right, great. It seems like we also have a few questions here. First one from Konstantinos. How the patch index accommodates the updates or deletions, and what about mixed workloads, read and write workloads? Great.
Yeah, so typically the use case as ActinVector is a OLAP database, so it the use case is for analytics. So we typically have bulk updates and not trigger updates like inserts. And as I said at the end, updates and deletions are ongoing work. So where we try to avoid that the index is fully rebuilt, and we also try to avoid a full table scan, as, for example, the uniqueness is a global constraint, where one inserted tuple may delete or may destroy the uniqueness of another tuple. And so this is quite a challenging task, but we aim at doing this in the future.
Mm-hmm. Quick follow-up before I move on. Can you say a little bit about the overhead induced from building the patch index? Does it take a lot of time? Is there a big memory overhead associated with it?
Yeah, so what we see in the evaluation is that, of course, you would not build a patch index if you would only query the table once. But let's say from two or three times, then you get a benefit from it. So the speed up is a trade-off between the creation time and the gained speed up. And so when you query it multiple times, then you get a benefit out of it.
Okay, I see. All right. Next question from May. NUC is a very interesting question. Can they be declared by user explicitly in place of conventional unique constraints instead of being discovered?
Yeah, of course. I'm sorry.
Yeah. So if so, is there a notion of NUC violation?
Of course, all the index definitions come from a DDL, so you can specify it as a user, or you can integrate it into a self-managing tool so that the tool can define the indexes. So you can do it by hand if you want. Yeah.
Well, I guess the key question here is, let's say we actually went ahead and declared a column as almost unique.
Yeah.
Would the system ever throw an exception? Would it say, if I enter 10 times the same value, it would say, oh, you've violated. This is supposed to be.
The interesting thing of it is if you declare a column as a unique and you insert a value that violates this constraint, then basically the system will reject the insertion, right? But if you declare it as nearly unique, even if it is fully unique, and then you insert a duplicate value, then it is assigned to the set of patches. And so it's not, even if your database is unique at the start, or your column is unique at the start, then it can be, over time, can get not unique anymore.
Right. So I guess the answer is there won't be a violation. You won't get an exception from the system. It would let you insert the duplicate and mark it on the patch index.
Yeah, and
Perfect.
That's basically an advantage over the hard uniqueness constraint.
Mm-hmm. So what other constraints other than key and sorting do you have in mind?
It could be constness. So that if a column only has constant values, or for example only a few values, so 2 or 3, then it might be that we can accelerate selections, something like that. So this is basically the index is generic, so any other constraint that might be of interest in query execution and optimization could be integrated in theory. So constantness might be one of it.
How about any constraints across tables? I don't know if Panus was thinking about foreign key constraints, for example. Could there be like a patch index for something like that?
Yeah, basically the uniqueness constraint can be used for this nearly foreign key as, for example, if we have a foreign key, then a hash join can be executed as a foreign key join, right? Because yeah, we will have guaranteed only one join partner. So this could be used as a potential optimization. If you define a patch index on the foreign key column, then you could exchange a generic hash join with a foreign key hash join. But as the benefit in exchanging these join operators is quite small, so let's say 10% maybe, or even less, we decided to exclude this case for optimization, because then the overhead is nearly not measurable, and also the speed up is maybe not that good.
So what about using this idea as a basis for approximate query processing?
Yeah, this might be an interesting thing. So if you, for example, you could, especially the uniqueness constraint, you can just query the patch index instead of the table to get a nearly unique result for a query, I guess. Or let's say you have how many distinct tuples are in a count distinct query, then you would also just count the tuples that are not excluded, and you have somehow an approximate result. But yeah,
right.
Definitely need some more investigation, I would say.
Cool, very interesting. All right, thank you, Steven.
Thank you.
All right, so let's move on to our final talk for this session, titled "Start: Self-Tuning Adaptive Radix Index" by Philip Fent, who's a PhD student at the Technical University of Munich. Philip, would you like to introduce yourself?
I'm saying some words in the video, so I think we can start with the video first.
All right, sounds good.
My name is Philip Fent, and I'm a PhD student at the Databases Group at the Technical University of Munich. Today, I'll present our work on a self-tuning adaptive Radix tree. This topic is all about database indexes, which are a core component to accelerate queries. Recently, the work of Tim Kraska on learned indexes really stirred up the world of database index design and kickstarted a lot of new and exciting research on using machine learning in database systems. This is a great development since this really showed where traditional indexes are bad. But our group here in Munich concentrates much more on practical index design, which still concentrates on traditional indexes like the adaptive Radix tree. We focused on practical indexes since we want to actually use them in our database system Umbra. So, learned indexes have the advantage that they are small and efficient. So they just fit better into caches. And they can adapt to all kinds of data distributions. In result, they're extremely performant for read workloads. On the other hand, ART is a widely used index structure in practice. So, for example, Hyper and DuckDB use it in production, and operations on ART are well understood and battle tested. So, we know how to update them with predictable runtimes, and we know how to synchronize them in concurrent workloads. And ART can handle strings as keys. In addition, also art is very fast for a large variety of workloads, even mixed read-writes. So learned indexes can much better adapt to the data and outperform art in several use cases. With our self-tuning art, we try to learn from the learned indexes and improve the performance for read-heavy workloads. So our goal was to adapt art to the underlying data distribution, which makes it much faster than a traditional art. We almost double art's lookup performance and bring it on par with learned indexes. But we still keep art's robustness for all kinds of workloads. Here you can see an example of an adaptive Radix tree. It has a typical tree-like structure with deep branches. To access an element, we first follow a couple of pointers through the tree, which we choose by looking at one byte of the key on each level. We then reach the correct leaf, which stores the value for the key. Since art is a Radix tree that uses 1 byte of the key at a time, a 3-byte key leads to a 3-level tree. To get a more efficient art, we want to have a more shallow structure. For this, we introduce multi-level nodes that use 2 or 3 bytes to shorten the tree traversal. The problem with this concept is that it is not obvious where we should use those multi-level nodes, and where single byte nodes are better. Also, it is possible that multiple multi-level nodes would make sense in the tree, but when they might overlap, so we need some way to make a decision which is actually better. In our work, we designed a cost model for our self-tuning art and implemented an optimizer that introduces optimal multi-level nodes. This process is an offline optimization step where we improve the lookup performance. So in a database, this might happen at regular index maintenance, something like a Postgres reindex, or the auto-vacuum daemon that runs every now and then. But ideally, the database system would recognize that the index is used for many reads, let's say in an index-nested loop join, and we then determine that it is worth it to spend some time improving the index. We implemented 2 multi-level node types. One approach that uses rewired memory for huge nodes. Those can be used for dense regions with lots of keys. For example, when there are subtrees of an art where many nodes have 256 entries of a bytes filled. The rewired nodes then can keep more of the data continuous in memory, so they can be efficiently accessed. We also present another node for sparse regions, but they only have a minor impact on the tree, since art already uses path compression. But sometimes there are still chains of small nodes with common prefixes that only vary by a few bytes, which we can reduce with multi-level nodes. So let's start with the rewired memory nodes. The basic idea is to use bigger Radix nodes. So instead of a node of size 256, which uses a single byte as an offset for the child pointers, we use a bigger flat memory node with 256 to the power of 3 children, so conceptually 64,000 node 256 with 16 million child pointers. Then we don't use a single byte as an index into the node, but we use 3 bytes as offset to load the child pointer. Of course, like this, those nodes have terrible memory efficiency. When there are somewhat sparse regions in those 60 million key bytes, we waste huge amounts of memory. We deal with the memory efficiency using rewired memory. To give you a small introduction on how we use rewired memory, let's look at a small example. We start with an anonymous in-memory file that's shown here in the middle layer. Then we map some of the pages of this file into virtual memory using mmap. So here we map the blue and the orange page directly to the first 2 pages of the file and write A and B. We then also map the green virtual memory page to B. Now the contents of the memory as it appears in virtual memory is different from the underlying physical memory. Here we get 3 pages in virtual, but only 2 pages of physical memory. This reduces the actual memory consumption. Following this idea, we implement our huge nodes and share physical pages between sparsely populated virtual pages. Here you can see the same mapping as previously. In this example, page 1 is densely populated, so it gets a whole physical page on its own. Page 2 and 3 are not that densely packed, and we let them share their physical memory. Since now they have the exact same contents, we need a way to recognize that the child pointer is actually from another page. For this, we use pointer tagging of the child pointer to store a part of the key. So as an example, let's say we access the element with index 19, which is on the 3rd virtual page. But this page is rewired to the 2nd physical page. So we actually load the element with physical index 11. But we still need to check if the tag of the child pointer matches the expected tag for an access from page 3, which is the case here since the colors match. But when we access the actual element 11, we would detect the mismatch since the entry belongs to page 3 and we know that the element is not present. In practice, the rewiring works really well. We observed one example where we had a virtual fill rate of around 1%, but only physical memory consumption of 23 bytes per entry, which means that roughly every 3rd physical element slot was filled. So, dense regions are well covered, but the rewired nodes by the rewired modes. For the sparse areas of the tree, we also implement a new multi-level node that holds only 4 elements. We designed the node to fill up a whole cache line, so each node stores up to 4 4-byte keys and their 8-byte child pointers, which helps with some prefixes or infixes that aren't handled well with prefix compression. The small multi-level nodes reduce chains of small nodes that would require lots of pointer chasing. Using these nodes, we set up a cost model that is based on the lookup for each node. Start uses a total of 7 different nodes. 4 regular single-level ART nodes in this table on the top, and 3 new multi-level nodes at the bottom. We now measure how long it takes to traverse each of these nodes in our start. We measure the latency for a lookup that is unique to each machine. So we run the measurements dynamically on the target hardware. We first measure the cached latency, which is usually the case for the upper levels like the root node. But some nodes are only partially cached, like the header of the huge nodes. And the lower levels are usually not cached at all. All these measurements form the base for our cost model, which minimizes the average lookup for each child. We then use a bottom-up optimization algorithm to calculate the average lookup costs of all the combinations of nodes which we could use. This uses the general idea of dynamic programming. So we first determine the optimal cost for lower level nodes, and then compare in the upper levels if we can get a more optimal configuration. To look at an example, we write down the costs for each subtree, starting at the bottom. The number on top of the brackets, right next to the nodes, shows how many children are in the subtree. And inside the brackets, we calculate the total costs for this subtree, which is the combined costs of the lower level nodes. So we start with the left subtree, where we just add the number of the children, 25. Then we add the costs of the 2 lower levels, which is 80. Then we also add the costs to traverse the top node of the subtree. With 2 times 25 is 50, plus 80 makes 130. We also remember the costs without the top nodes in case we can use a multi-level node that can skip this one intermediary node. On the right subtree, we do exactly the same and get 15 children with cost 85 with the middle node and 55 without. So now onto the root node. We now combine the information and try if a two-level node would be profitable, even if it has a higher cost of 3. We again start with adding the memoized costs of the subtrees. 1 skipped and 2 skipped. 80 plus 55 is 135. 130 and 85 is 215. Then we use those calculated numbers to decide if a one-level node with traversal cost 2 or a two-level node with traversal cost 3 is better. 40 times 2 plus 115 makes 295, and 40 times 3 plus 135 makes 255. So we get fewer costs with a two-level node. Of course, this is just a simple example, but our optimization algorithm will produce the best multi-level start tree, even in complex situations with more combinations of multi-level nodes. The performance gain also shows in our evaluation. Here we use the search on sorted data benchmark, which provides a variety of different datasets and measures the lookup latency. We compared start with 2 publicly available indexes, Radix Spline, RS, and the recursive model indexes by Tim Kraska. The experiments here are single-threaded, and we measured the latency, so lower is better. Compared to the baseline ART, start is a clear improvement over all datasets. For all datasets, we were 85% faster. On this particular subset, we only get a 55% improvement. But what I want to point out here is that we even beat the RMIs for many datasets. So here, for the Amazon book datasets, the Facebook user ID dataset, OpenStreetMap's location cell IDs, and Wikipedia article edit timestamps, start is the fastest index. For synthetic generated datasets, like the data following a normal distribution or the uniform random dense data, RMIs are still a little bit faster, so there's a little bit room for improvement. To conclude, with start, we think we can combine the best of both worlds. We improve art to adapt to real-world datasets, but we still kept the robustness of an art. In our new nodes, insertion is still possible and is also efficient. Only when there are lots of insertions, we might need to split the multi-level nodes again. But we still get graceful degradation to a regular art. We publish all of our code on GitHub under the link on the slide. For any questions, you can write me an email to fent@in.tum.de. And if you're following SMDB and ICD live, I should also be available for Q&A right now.
All right, great. Let's see, we have our first question now. In the graph, you plot NS over op. Can you explain what you count by op, operations on the structure, or what does op mean?
So the operation here is a lookup. So we have the nanoseconds per lookup. So the time we consume to access an element in the index. And on this graph, lower means better. So yeah. We also have a benchmark of write operations in the paper, and that's where I got the slide from, and then operations make sense.
Mm-hmm. Actually, I also have a question. You mentioned at the beginning that well, currently you're using an offline optimization, and we see a bottom-up optimization algorithm. What would you say is the biggest challenge for turning this into an online algorithm so that you can adaptively, let's say, decide or maybe switch between, the multi-level part of the tree or shift different parts of the index around?
So I think since we're trying to be practical, when those huge nodes, we need to lock a whole subtree of this art. So, and when we reconstruct this whole subtree of the start, then this can potentially take a lot of time and block transactions or so that are accessing this subtree. So we need to have some kind of decision algorithm when this makes sense. And I think in an offline scenario, this is much more practical than performing this online.
Mm-hmm.
If we have more smaller nodes that can be introduced more easily with less locking, then I think it makes sense. But this is still an ongoing research topic.
Perfect. Is there a clear trade-off between memory utilization and the overhead of virtual to physical mapping?
Yes and no. So to introduce those physical and those virtual to memory to those mmap mapping from virtual pages to physical pages, this scales with the number of mappings we need to do. So when a lot of pages share other pages, then this overhead gets longer to introduce this mapping. But as soon as we have introduced this mapping, then there's no overhead at all. So that's the beauty of this rewired memory, that the memory management unit takes all the performance overhead of this rewiring from the application. And this is a very cheap operation to look up a rewired memory page.
Mm-hmm. Great. I think we're officially out of time. Thank you, Philip. Great work.
Thanks for having me.
Mm-hmm. So I guess we're taking a few minutes, a short, let's say 5-minute break. And then the second keynote of SMDB by Sandesh Rao will take place. Thank you all for attending the first research session, and stay tuned for more.
Hello, everyone.
नहीं करी होंगी अभी
Okay, hello everyone. Welcome to the afternoon session. No matter which time zone you're in, this is the start of the afternoon session. We're very pleased to be able to offer this keynote jointly with the HeartDB and Active Database workshop. And we are honored to have Sandesh Rao from Oracle to present a presentation on AIOps with the Oracle Autonomous Database. Sandesh is a vice president running the AIOps automation for the Autonomous Database group at Oracle. And he's been working on using the AI or machine learning techniques for different use cases. And that includes predicting faults before they happen, and anomaly detection with big log data or metrics data. He has over 18 years of experience working with various products, and especially focused on performance tuning, high availability, disaster recovery. So with those kind of experience, he's able to then apply AI techniques to solve some of these problems, especially as cloud-based solutions. So at this point, I will then hand the podium over to Sandesh, who will share with us his experience and solutions in this area. Thank you.
Thank you so much, Mishan. Panos, editors, thank you guys for the opportunity to present. I'm going to go ahead and share my presentation here. I'm assuming you guys can see this. I'm not going to go into PowerPoint mode because this kind of messes up my extended display. So I'm going to stay with this. If you guys can see this, I'm going to continue with this. So first of all, I hope you guys are all doing great. This is a great opportunity to talk to people from the field who basically understand some of this stuff. My name is Sandesh. As Mishan mentioned, I've been in this space for almost 20 years. I've actually, the two key roles I've been doing in the last couple of years. The first one is AIOps, where I'm actually responsible for the entire stack that basically ingests all the data that comes from the database cloud services. And we do all sorts of interesting use cases with them. There are hundreds of them. Of course, I have 45 minutes. So I'm going to try to crunch this stuff to give you as much information as I can in the time limit that I have. I'm also responsible as a focus area lead for all database diagnosability, which means everything that comes from inside the database, whether it is AWR, whether it is metric information, whether it is optimizer information for cardinality, better cardinality detection, all the talks that are part of this conference, I'm kind of touching these topics in some way or the other. So it's just truly exciting for me as well to kind of see what other perspectives people have. But that's my background on this. So with that, I'm going to get started. We have to have this. That's me. So the conversation today is going to be on around 4 areas. Okay, so basically, what do we do for the AIOps platform? We're going to focus on use cases. Use cases are interesting because they're the best way to illustrate as an example of what are the real world scenarios that we're basically trying to use this on. And I'll try to go as in depth as I can, but please understand each of these use cases is like a 2-hour talk in itself. Pros, cons, and what other things that you can do. We're also going to talk about what algorithms, tools, technologies we use. Some of this stuff is within Oracle we use, but we also make use of a vast swath of stuff on the open source ecosystem and all the data science cloud that we have. So I'll give you an idea of not just what we build, but how we build it. And we'll have some time for questions and open talk. I'm assuming it's lunch after this, so we may exceed the lunchtime period. So I'm hoping if you want to stay with me for an extra 10, 15 minutes and ask questions, I'm going to hang around. All right, so everybody knows this, that data is basically the new oil, and everybody's working on this stuff. Why is machine learning all of a sudden so cool? It's because we suddenly have the enormous hardware and software capabilities to be able to take all this stuff, to be able to stick it into VMs, to be able to process this using large machine learning frameworks, to be able to use libraries that somebody has basically spent 5 years of a PhD building, and then we basically take this and convert this into a library that can just be called by a simple API as a software developer, where people do not need to know how these functions work. there's a lot of already pre-existing work that's been done in this space, as a result of which it makes it very easy for someone today to get started in this machine learning space. And obviously, if you want to get started with something, it's as simple as a Docker init. You can set up a Docker sandbox with most of these algorithms, and you can get started with it. We make use of some of our Kubernetes cloud services to spin up containers quickly, run a specific task using machine learning on a piece of data that sits across our object store or across our messaging services, and then we shut the thing down when we are done. So we can spin up millions of containers every day and shut these things down as we need to process things. What is AIOps? Now, some people know about this, some people don't know about this, but it's basically, think about it as DevOps that you do on a stack. But normally people are kind of running around and trying to figure out, looking at all these metrics instead of looking at these metrics manually and trying to make a determination of what is going on in the system. We basically use AI to understand this. A lot of this stuff runs off the actual system where all this data is generated. So there was a lot of conversation earlier about, hey, should we run more AI in line? So we'll discuss some of those pros and cons as we go through some of these use cases. But most of this stuff runs actually off the system, live system, where the data is actually generated. And we've developed some telemetry capabilities to be able to push the right appropriate data out of the system. If you push all your data outside the system and try to analyze it using AI, it loses its potency to be able to analyze things on the fly and come back enough in real time to be able to prevent a fault. So you have to, it's like a research, right? How long should you be researching this? It's not like you should research something and then by the time you're ready to ship it, that technology is obsolete. So the same thing applies to AIOps in a circle, where whatever you process, that data has to be relevant within the time period of the event that it's actually supposed to monitor. So the things we're going to focus on in this talk is detecting degradations and faults, pinpointing root cause analysis, how do we look for duplicate issues, and how do we track SLAs and on metrics like that, and how do we try to repair this as much as we can using a combination of automation and AI. So it's not all AI, it's a combination of automation and AI. Some of these use cases do not need anything more than a simple rule-based system for analyzing some of this. A kind of rough architecture of the AIOps stack that we use. We have we do a lot of the machine learning and the training for all our models. Then we have all the machines on the customer VCN where we mine all this telemetry data and we push this data out to something called the Autonomous Health Framework Service. What this is basically the central location where all of the processing happens. It's not a machine or set of machines. It's actually a service that spans multiple cloud regions. So most of the data processing, most of the heavier data processing for anomaly detection and all of these kind of tasks basically happen in the AHF service. And then we have a notification service. It's actually a lot more than just a notification service. It's a metric collection service. The metric collection service provides the capability to build dimensions on top of everything. An example is CPU consumption for a specific server. Imagine you have 100,000 servers in a data center. You streamline the CPU consumption for every one of these things, and you push this into a metric extension. And after that, you mine and build dimensions on top of this. So all the processing can happen outside of the server, where the server's task is just to push out all this information. You also have to be very selective in what kind of data you push. We have Jira and PagerDuty and CloudOps, which is basically our ops organization that takes a look at all these things and decides what they need to do for this. The Jira and PagerDuty, of course, these are universal tools that are used for ticket management and Pager in case somebody has to actually go and pull a physical cable or replace a disk or do something like that. Most of the tasks in this are kind of automated. So there's literally none or very little human intervention as far as that's concerned. A little bit more into this, what are the kind of data we actually pull out for this AIOps platform? The database generates a whole bunch of stuff. Now this is for primarily, I'm giving the example of a database cloud service. So it's a combination of databases, hardware, switches, things doing RDMA around. So you have to pull all sorts of different logs and compliance and health data into this telemetry infrastructure. So the alert logs are basically like a sequence of timeline logs that tells you what is happening within the database infrastructure. There's compliance data, which means something is either not adhering to a best practice or something that's violating a rule, whether it's SOX, HIPAA, or any of these things. Then there's health, availability, performance, and capacity data. When am I going to run out of space in this table space? When am I going to run out of space in this disk? When am I going to run out of space in this object stored infrastructure that this thing is pushing. So capacity management as a whole for all components within the cloud, not just each individual component. And as well as performance and availability data. Which thing is down, when is it up, how long does it take to come up, how long is it staying down, does it impact any customers, all this sort of metrics. So basically this is extremely heavy instrumentation of almost anything and everything that happens within a database cloud service. So the first step to building something like this is instrument everything. Take every piece of metric you have, whether it is CPU consumption, memory consumption, network consumption, disk consumption, or whether it is a system is up, a system is down, a database is up, database is down. We push all of this information out into a telemetry service. We scale this stuff using our object store and a combination of our messaging service, which is basically a Kafka-based service. So we can take this information, store petabytes of it, replicate it across various data centers. And we, as a AIOps stack owner, I don't have to worry about the resilience and the availability of this data because it automatically gets replicated across all of the data centers when we build this. We'll go into examples. This is the best part of the talk, and this kind of makes more sense when you see this as to how do we use AI for some of this stuff. And we have like hundreds of use cases. I managed to pick about 5 or 6 of these that kind of make the most sense for this audience. And you'll see how we use some of the algorithms for this. So the first and the most important thing is whenever you have an enormous fleet of databases, as in this case that's running, and there's a combination of databases and it's a combination of hardware, you need to take all this log information, which could be like hundreds of petabytes of log data in a year. And we have to figure out from this log data, which is the most important events that a person needs to look at. Now remember, some of these use cases I'm talking about requires no human intervention whatsoever to recover from. And some of these require some human intervention to recover from. But as an average, most of the issues in our cloud, more than 85% of the issues that we encounter can be resolved automatically by using some kind of an AI service that we have built. The remaining 15% require some sort of inspection. Some of them are inspection and some kind of action has to be taken. Some of them is just for inspection to say that, hey, this thing keeps degrading, something else is going to happen. So we classify all the events into something you need to look at right now or something you can look at later. And 99% of the stuff goes into something you can look at later. So unless it's something that's extremely important, it does not bubble up. So how do we do this? Now, this is one of my most favorite use cases, and it's basically anomaly detection on top of data, on top of log data. Okay, this can be any kind of log data. It can be databases, it can be var log messages coming from servers, it can be networking data, it can be web server logs, it can be any sort of data. Now there's a lot of stuff out there in many different frameworks that can analyze and process and massage and build indexes and all that stuff. And there's some sort of knowledge around this stuff. The thing that's interesting is for us is we've actually gone and taken all this log data, ran this across using a semi-supervised machine learning algorithm, spend some time with each of the developers that are responsible for generating some of this log data, and use them to train some of these algorithms. So the result accuracy of this thing is pretty cool. It's pretty darn accurate. So the process or the steps are, we basically take some percentage. So while there's a lot of AI involved in this, there's 2 steps to this whole process. The first one is you selectively pick only a small amount of stuff that you need to take out of the server. That's less than 2% of the data that normally is that you would normally pull out is what you need to stream out of the server. That itself runs into a couple of 100 petabytes in a year. Once you take this log data, you build, you perform, of course, feature extraction, which means you have to extract entities out of this log data. You have to find out if this log text is interesting, how many defects have reflected this information. Let me just quickly step ahead to this one. This kind of makes sense. So you create the entry features by extracting all this information from the log data. Usually we have about 80 to 90 features. After performing some kind of dimensionality reduction, we basically come down to about 15 features, which are adequate enough to basically tell me that if these log lines are interesting or not. Then what we do is we perform entry clustering. And by entry clustering, meaning a lot of the log lines have just 1 or 2 invariants. So we just basically try to take this and say, okay, these log lines look similar. We can just combine these log lines together to say this one represents the same kind of metadata. And we are building a knowledge base as part of this process. The knowledge base we build here is of course using entropy. We use Shannon's entropy theorem to basically build to calculate the entropy for each of these individual nodes. And this is using simple decision tree classifiers. Now, we've tried to use all sorts of complicated stuff from LSTM, LSTMs to random forest to decision tree classifiers. And this one kind of works the best. So one kind of basic theme that we have and that we use is if a basic classification algorithm is adequate for doing something, we don't have to go forward and use a deep learning algorithm. So we use the right algorithm that is required to solve our task within the efficiency of which the task is required to be solved. We don't bother using a deep network if it's not something. There are many cases where we've used LSTMs and these LSTMs take forever to train as compared to using a simple classification network. So we've kind of spent some time on this, and we've come to this conclusion, at least for this use case, that a simple decision tree classifier works really well. We have an initial label data set. We take this initial label data set, we use it to train the initial data that goes in. So we establish spatial and temporal references related to these anomalies. And when you compare them across all the various kinds of components, right? Now these components are different. They're not database components. There's database components, there's clusterware components, there's ASM, which stands for Automatic Storage Management, which is a software that we use to distribute data across various kinds of disks. So it's disk management. They all write at the same time, and you have to use this algorithm to basically train it to establish a correlation, whether it's a spatial correlation or temporal correlation across all of these log files. Once you do this, you generate the model, then you need to compare this. Of course, we use expert input, as I mentioned, because this is a semi-supervised machine learning algorithm. We go back to the developers for the individual areas, and they help us train these areas to ensure that what data we display as part of the anomaly timeline is accurate. Once this is complete, we have the knowledge base, we index it, and then we need to compare this against every log line that happens. So remember this, if this knowledge base is an approximate, can have about 60 to 70,000 entries. From this, we need to compare every log line that gets generated from every server that we filter, which is 2%. Remember, it's just barely 2%, but it still runs into a couple of petabytes of log data. And it needs to be near real time to basically tell me that this thing is good or not, or is this going to be a fault or not. So it has to come back within like a second or two to tell me this is interesting or not. Otherwise, it's no point comparing this thing. How do I run an inference engine on the system without consuming a load of CPU, or without actually doing any kind of training? So by the way, all this training happens on some sort of a remote system. Only the inference engine is running on the actual live system itself, because we don't want to consume enormous amounts of CPU just trying to learn on the system as the problems happen. So what this thing does is we use TF-IDF to score the log lines. So what tends to happen is each and every one of the, so we take a line of text and we split it up in variants, with how many of the tokens that we have, and each of these tokens is assigned a certain score using TF-IDF. Once we build a TF-IDF index, we can set a number saying anything that has a TF-IDF score of less than, say, 0.04. We pick a number just to know, just by looking at these log lines, we know that which ones are interesting, which ones are not interesting, and what is a good threshold score for this TF-IDF number. Once we build this, we can say that anything less than a TF-IDF score of this does not need to be compared to the knowledge base. So we avoid a complete Cartesian product of the knowledge base with every log sequence that basically comes into the system. By doing this, it increases the efficiency of our algorithm 20-fold, because we can scan a lot more log lines without actually having to compare anything and everything against this. So the net result of this thing is like this. You take a whole bunch of logs, you punch this into the system, and then you build this anomaly timeline, which converts like a couple of gigabytes of log data into 3 pages of actionable information that we need to look at whenever we are troubleshooting a specific problem. Now, the smarts is not just only in the algorithm. The smarts is also in the database where we have, we basically spit out signatures for all sorts of faults that we write. These signatures tell us, without actually having to look at the stack trace or any other information that's outputted by this particular process, if this exception is a similar exception to anything else that is actually generated. So imagine I have 500 exceptions in a log, and all of them are the same. They have the same signature. So I only need to look at the first occurrence. And then based on the signatures and a combination of this anomaly timeline, I can quickly zero down to just the essential amount of stuff that I need to see as a human if I ever have to evaluate this for root cause analysis. So it'll take us like 5 minutes to generate a root cause analysis of something that used to take hours or days, because you have to piece in all this information from all the various components that come into the system. So this is sort of like what it looks like, right? So it's like, it shows us all the interesting stuff. It shows us from the various logs, including the exceptions that they have. And it uses a color gradation. As it goes towards red means something is starting to fail. And it's pretty self-intuitive for somebody that's actually trying to troubleshoot this. There are also cases where we use each of these use cases to feed into each other, where we have the capability to say that you can feed this anomaly timeline use case into this signature use case, where we detect certain examples of problems without having to go into details of this. So not all of this stuff is human inspection. Most of the stuff can actually be made completely automated, and these use cases can feed into each other. So this is the first use case, which is clean the logs, analyze, cluster this to generate a model, use the developer experts to train this using semi-supervised machine learning. Once you do this, you ship the model gets updated once every week. It's usually good enough for that. Identify anomalies, and we also identify OS anomalies, metric anomalies, and we kind of put them all together in the same graph. So that allows us to look at stuff and say, oh, there's something going wrong across all of these entities. And it automatically updates our tickets if interesting analysis is found, so that if anybody human were to go and look at these tickets, all this stuff is already updated. So this is the first use case. So this is sort of like what it looks like. So this is when you combine log data along with different kinds of metric data. So it just highlights here that, hey, when you're running this, there's this value that's been found, and this is the mean for this value along with log data. So it's very interesting for us to look at different facets of the problem when you're trying to troubleshoot something. The second use case, this is actually pretty interesting for us, is predicting what the CPU usage is going to be in the future and to detect anomalies. Now, remember, this is a topic for probably another day, is one of the most interesting things when trying to develop something using cloud is placement algorithms. Like, how many clients should I take? Where should I put them? Should I put these 20 clients? It's basically the packing algorithm that flight companies deploy, right? Where to ensure that they don't have to throw somebody overboard, but at the same time, they try to pack as many people into a flight as possible to maximize the revenue that they're actually having per flight. It's very similar. With the placement algorithms, they kind of dictate for us to be able to pack as many sessions without actually seeing degradation in any of these sessions. So we kind of have to pick users that are not kind of active at the same time and users that do not burst CPU significantly enough. Now, when you do this, the input to this algorithm, the initial placement is very easy because based on their current usage or based on, say it's an old customer, you know what they're going to do. But if it's a new customer, there's no way to predict whether they're going to use up the entire machine, they're going to request for more CPUs, are they going to burst more often? There's no way to know this. The important thing for a placement algorithm is to be able to predict what CPU consumption you're going to have in the future. So what we do is we monitor. So there's a repository inside Oracle, it's called AWR and ASH, which is Active Session History and Automated Workload Repository, which basically collects or instruments data corresponding to performance for an entire database. What sessions are there? How long have they taken? What wait events are they waiting on? All sorts of stuff we track. Now, what we do is we use this in combination with, we have the ability to resource limit certain sessions. We put caps on certain sessions. Like if someone says, I'm buying only one core, I have the ability to limit them to a single core. But when they exceed that core, I also have the ability to go look at what this person is exceeding and could this person benefit from twice the number of cores, and then burst them down when they no longer need those cores. So how do you combine resource consumption, try to predict resource consumption, and feed this into an active placement algorithm? So this is actually a combination of two use cases. I'm not talking about the placement algorithm. I'm only talking about monitoring database workload. And many speakers before me have covered database workload and using AI and machine learning for database workload as an interesting use case. This is very useful for us because we not just can predict resource usage, but we can also predict capacity shortage long before it happens. Now, you might think, hey, but this might take some time to build. The answer is yes, it does take some time to build because each user will have their own kind of workload. As a result of which, you need to think about what this person is going to do even though you may not have enough information about the workload for this particular person. So how do we do this? So first of all, we push all the telemetry information out for capacity data out into our service so that nothing happens on the box. A simple example, I'll give you one of these use cases. We have at least 6 or 7 different ways of solving this problem. But a simple example is using something like Holt Winters for triple exponential smoothing to find out when a particular use case is interesting or not. Now, the first thing you do is you basically use some normalization algorithm. In this case, we start playing with boxcox to normalize this data. And this happens when you have multiple features and you kind of want to prevent distortion of the impact of any of these features that have sudden spikes or sudden large values. You don't want this thing to completely take your forecasting off the charts. And what you do is, over a period of time, you just try to pick the observed values, and then you forecast this using an exponentially decreasing weighted average of all the previous data points, which means the more recent a value, the more higher the impact it's actually going to have on what you're looking at. Then you basically go for the second one, which is the second level of smoothing, in where you can dampen the trends, as you basically use, again, an exponentially decreasing weighted average to calculate this particular trend. This is the second level of smoothing. Once you do this, then you have to take into factor the seasonality. This is standard for any kind of time series data processing that you can use, but this is actually very effective for database workloads. And again, you try to find out what sort of seasonality or what sort of seasonality components you have in this, and you multiply that or to the trended values that you have based on your seasonality factor. Once you have that, you have a better idea of forecasting, but that's not enough. Then you take this and you feed this into something called a grid search walk algorithm, which provides error calculation for you, which means it tries to figure out what you're doing and what are the errors in your pre-calculation. So the algorithm actually gets better by including your forecasts and going back and saying, did I forecast this right or not? So this is sort of like a reinforcement learning algorithm, but it works pretty well in Holt Winters. Once you do this, you basically use RMSE to figure out which one, how close were you to predicting this value. And this is sort of like what it looks like, right? So once you predict all this, for each of the instances, how many cores that they have and the sizing recommendations for these cores. The green values are what we are predicting will be consumed. The blue values are what are actually consumed. So it's kind of pretty cool, and it allows us, so if you take this for every CPU that's actually in the system and you combine these results, I can exactly predict for a combination of a server, how much CPU the total server is going to consume based on the workload running on that server. So remember, this algorithm is very specific to that server. Because client workloads can vary significantly, and one client may not do the same thing. But what this is geared to doing, an example is a client comes on Friday morning and fires a workload, which gives 100% CPU for 5 minutes and then goes away. So I know that this client does this. But I'm a DBA, say, for example, managing 100,000 systems. There's no way for me to physically remember this. This is how people used to do things in the past. Oh yeah, I know that user, so that's okay. But in a cloud, people can come in and do anything they want and they leave. So there's really no pattern to this sort of stuff. So this algorithm takes, I think, about a day sometimes to kind of figure out a pattern in what that user workload is. And once that thing kind of hardens up and the user becomes more predictable in terms of consumption, this helps us predict CPU consumption usage, and it also helps us with the placement algorithms and to improve the packing factor. We can put way more users on a machine without actually depriving any users of the kind of resources, even if they all chose to go to 100% of whatever that they're choosing to consume. Based on their, like, some users will have end of day on March 31st for taxes, some will have it on March 30th, you combine the two together. So you know that they're not going to use it at the same time. So the second use case combines all this information and applies it for the placement algorithms. The third one is an interesting one. We don't do plan maintenance unless the customers ask us to do it. But the thing is, there's a lot of small, tiny tasks that we actually can do this. And we use historical data, and we tend to apply a convolutional filter, and we average this information out, apply seasonality to it, and it tells us when the user is basically not using the system as often. This is a lot more complicated than what I've illustrated this here, because there are many, many conditions as to what happens inside the database systems, what happens outside the database systems, what calls are there, is the maintenance activity I'm performing, is it complementary to the task I have in the database, or is it conflicting? So for example, I can't apply a dictionary patch when someone is performing some sort of a SQL that's actually using those dictionary components. So there's a lot of other considerations apart from just this. But a good example is this is like, when should I fix pavers outside your house? So now I know, okay, there's COVID and everybody's going to be sitting at home. So I know that, you're not going to come out of your house for a day and I can quickly fix the pavers. So there's a lot of tiny maintenance tasks that do not require complete downtime that can result in a 2 to 3% performance degradation across the system. And we use this to detect if this is what we should be doing or not. So this is maintenance windows. And this is sort of like the original data. This is the trends, this is the seasonality, and that's kind of what the final curves that we get for the residuals. And based on the residuals, we can decide which servers to do these. And of course, these maintenance tasks are automated. So it's not like, hey, is a human available to go run this stuff now? Those tasks, they need some downtime, and we have to take permission from customers before we do them. But there's a lot of tiny tasks that do not. Another one is, this is an interesting one. We use this use case to just detect anomalies. They're just metric anomalies. We don't use this for fixing them. We don't use them to find root cause analysis, none of this stuff. But this is kind of like something we just started playing with. It's a simple thing. Everybody knows about this stuff. It's a z-score. It's basically just a measurement of standard deviation from the mean. But it's incredibly powerful because it allows us to compare different entities that are not comparable, like compare network performance to disk performance. So how do you compare apples to oranges on the same scale and say these two are, when these two happen together, there's something actually wrong? So what we do is we take these metrics and we basically calculate z-score factored spikes. So what tends to happen is the larger spikes, they basically show unusual values. As compared to seeing everything, you see just the pieces of data that you want to see. Now this is CPU. Here's an example of memory, just to look at the spaces that you have to look at. And then it's like, if I'm looking at multiple metrics, right? If I'm looking at swap consumption, I'm looking at memory consumption, CPU consumption, I'm looking at procs waiting for runtime because the procs are in some sort of an interruptible sleep. These are different values that I look for to see if a system is toast or not. So what do we do is we calculate z-scores across all of these values. In this case, it's a z-score for run queue, context switches, CPU IO weights, and stuff like that. Now, what do we use all this stuff for? We try to find windows. Whenever we find a window that basically has too many z-score events happening with the same, of course, there's some sort of scaling that is applied to each of these values, so they kind of come on the same scale. And this tells us that if a box is in trouble or not. And I'm talking about a box, I'm not talking about just a server. I'm talking about an entire rack of servers. We take all these values. Now remember, we have thousands of racks of servers. And we're looking at this stuff. And this is like a red or a green light on a server rack. And it uses a weighted average of all these individual z-scores to tell us that if something is wrong on the server or not, on the entire rack or not. If I don't see these values, I don't look at the rack. I don't care about anything else that happens on the rack. This is that simple as that. So if there's something wrong on a rack, these values have to reflect it. And these values need to be persistently reflected over a period of time. It cannot just be, hey, this is 100% CPU consumption on one of the servers is not going to trigger this. It has to be across the rack. It has to be an event that's going to affect multiple customers that basically triggers this. So this is kind of like, instead of looking at time series graphs on some sort of a dashboard using Kibana, we can actually see some of this stuff directly and say, okay, this is a problem. This is going to become a serious problem. This is what we need to do to fix it. So this is what we use to identify, or one of the methods that we use to identify if something is seriously wrong with a set of servers. And this is basically fleet level intelligence. So you don't have to go into each and every individual system to figure out what's going on. If you're debugging a system and you're going into it, it's already too late. Problem has already happened. The first goal is to get the server back up and debug all this stuff later. So this is called z-scores, and we use this to detect faults happening across different pieces of infrastructure. This is an interesting use case. It's actually one of the most powerful things we use, and it's called an adaptive bug search. Now, what this does is, and this is basically what takes care of 85% of the issues that happen on our system. Any existing known issue, there's an automatic adaptive bug search model that looks for existing signatures on anything that happens on our system. It looks at the exception. It automatically looks for certain characteristics of the exception. We use very simple logistical regression on this stuff. And what it does is there's a certain set of input attributes that we use to train this, which is error stacks, trace stacks, problem descriptions, and any sort of bugs that are related to existing bugs that we have already found. They're all correlated together in something called a bug tree. We use the characteristics that we get from what customers describe the problem as, and then we combine those characteristics with the features that we have defined in this, which is error stacks, trace data, problem description. And then we try to find out which particular bug is at the root of this cluster, which is the bug tree, and say that this is most likely a duplicate of this. And then there's an automatic feedback mechanism where someone can go and say, look, you said it was this problem and it was not this problem, and they can flag it and the algorithm goes back and self-corrects itself. So a simple use case of this is a server could have a problem, an exception gets generated, there's a stack signature in place. Along with the stack signature, the stack itself, and a whole bunch of problem description information, we create something called an IPS package, which is basically a package that contains all diagnostic data for a particular exception. It's very structured, so it's very easy to deal with this. Once we feed this into this model, we can say exactly if this kind of problem has been encountered before, where it has been encountered, which release there's a fix in. It's all programmatic. And then automatically, if the server is not in a release where this problem has been fixed, it gets scheduled for a patch application. This is an interesting continuous iteration cycle. And this use case single-handedly takes care of about 85% of the issues that we encounter on our cloud with zero human intervention whatsoever. So it's called the adaptive bug search. It takes inputs as error stacks, trace data, log data, IPS package data. It uses simple logistical regression to basically build these models. It works across at least 400 of Oracle products, 400 or so Oracle products, and is expandable to any product. And once we do this, we have the ability to go back and see if an issue was closed, and say, for example, the same issue happened in the system where the patch was applied, we have the ability to go back and recorrect the algorithm saying, this is a decision you made with a confidence score of 0.95 and this was not right. So, and that feedback is also automatic. If the problem occurs again after a patch has been applied, after a decision was made by this framework. So it's pretty cool. So this is single-handedly one of the things that saves our bacon on a daily basis. I need to speed up a little bit. We have this other thing that we are still playing with. This is pretty interesting. So this starts off with and somebody spoke about this earlier, which is basically using the smallest common subsequence, basically using sequence matcher data to try to detect problem event path signature. And we try to establish about an 85 to 90% signature matching using sequence matcher to figure out if something is similar or not. The way this works is actually pretty simple. LCS for anomalous entries. It tries to classify anything as exceptions. It tries to look for these exceptions among multiple logs. Once you have these anomalous entries and lifecycle entries within a predefined period of time, it tries to say that these are repeated entries. A very good example is this one. This is just an example of a log file which contains basically this is basically what we use to build the FSA or the finite state automata, along with the knowledge IDs that correspond to these individual files. And then we basically try to establish a signature saying 5 minutes after the central event happened, all of these other events happen. So for every individual log line, there's an ID that gets created. And then we use this to build signatures. There are several different technologies that we can use for this. HTMs are a very promising piece of technology. LSTMs can also be used to detect and predict these signatures when they happen. We use LSTMs to generate these signatures. Once these signatures are generated, it's a simple comparison against the signatures that are already there. So there's no machine learning after that. So the process of generation of these signatures, so based on, it's like, think of it this way. I'm driving out into the freeway. Based on this time and this place that I am now, how long is it going to take me to get onto the freeway? Once I am on the freeway, I don't need that decision making anymore. So this is sort of like what it is. The signatures are created using AI. Once the signatures are established, it's a direct comparison against what's already happening. So we know that this is going to happen if this has happened 5 minutes later, this server is going to go kaput. So we need to start moving the tasks from these servers to other servers. So this is what we use this for signature comparison. One of the main interesting areas for us is database performance, of course. Whenever there's any kind of performance issue, we collect a ton of database and OS data. One good thing for us is the database is very richly instrumented with all of this information. So it's fairly easy to identify a specific fault. So there's a whole bunch of technologies we use in this. We use, mainly it's all Bayesian networks. Surprisingly works very, very well. And then we try to find out if a particular component is causing a fault or not. For each and every value, we have a certain fault classification. These are not threshold-based validations. These are validations that happen on a system. And these models learn on the system to establish these thresholds. So the models themselves are not trained on the system, but the models learn what the thresholds are on the system adaptively based on the kind of problems that it sees in the system. So it knows that, hey, for example, if you have a latency of more than 2 milliseconds in this, oh, you're probably running a hard drive, this is what it is. Or if you're running a latency of 200 microseconds, it's probably an SSD, so that's what the latency is. It's automatically smart enough to do a cycle of semi-training sort of on the system to establish these thresholds. Then these thresholds become adaptive based on the problems it recognizes. And it can take these values. It's part of something called a normality model. Now, this is for all database stuff. Like if there's database performance issues, if I'm running to log file sync waits, if I'm having user commit problems, if I have a disk that's not able to keep up and I start seeing a pileup of all these events, if my IOPS start dropping, this is kind of used to compare a normality model on a server and tell me if the server is starting to misbehave. And hence, this is from a database perspective. The previous one I showed you was Z-scores, which was basically from a systems perspective. This is a database perspective to look at what's really happening inside the system. I mentioned workload, but there's another aspect of workload that we did not discuss that I wanted to talk a little bit about here. So one thing that's interesting is we know that a customer's workload, we know when they hit thresholds, and we try to take action based on that for placement algorithms. That is one use case. This is the other use case where we actually just track the customer's workload. Workload is a very complex problem. Every workload is different. Every way to measure a workload is different. So what we do is we capture certain metrics which track wait events within the database, and we report this, and we apply three simple algorithms against it. And once we figure out if these things have at least 7 days of data, and if it's at least 92% accurate for a model, then we understand that we have to take a snapshot of the system at this point in time in terms of like the anomalies that we have detected for this workload and raise it as, hey, this is something that somebody has to inspect. This is really hard to automate. So if I give you a very simple example is, like if you're using your machine and say your machine hits 90% CPU utilization, you can't get any work done. But I might be another kind of user where I want to run my system at 90 to 100% utilization, so I can go back and tell my boss that I am, taking the maximum amount of money for what I paid for as far as software licensing was concerned. But I might not have as much of a great performance as far as what it is. So different ways that people look at workload. The goal of this is to establish an adaptive baseline using the workload information. And after that, I try to establish a threshold on top of this adaptive baseline. As an example is, I have an established baseline of, say, if a server goes above 85%, I know it's kaput for this kind of database workloads. And then I set up a threshold that if you violate this by 20%, then you have to start flagging this. These alerts can also go to a user that you're not basically doing things efficiently. You should probably scale up or double the number of CPUs for this task and then scale them back, because we have adaptive scaling where people can turn things on and off. So this is just purely tracking customer workloads and telling them if this workload can be efficiently done by allocating more cores, because some customers have a fixed number of cores and they don't want to allocate more cores, but with the optimal balance of making it efficient in terms of cost. So this is what this model is used for. And we try to detect all these unusual anomalies, and we broadcast whatever future values that we are going to see here. And this is sort of like how we display this. So these are all the various kinds of events, and then there are CPU bound events. So this is sort of like a dashboard where I can filter by servers, clusters, hosts, availability domains, and I can look at these events, and they look this simple, and I can click on it and say this particular server was using so much. And I can either comment on this or click on this and send this link to somebody else to look at, or I can say, hey, I can post this directly to a customer saying, you should look at this. Perhaps you could use more CPUs. I know there's somebody already talking about this. This is an interesting topic because we use reinforcement learning for our own index identification, where we can basically capture. This is a topic in itself. But the interesting part here is we can capture, identify, verify these indexes. We have all the information in the Oracle database. We have the cardinality. We know what sort of we have advisors that can predict what the cost is going to be if this index were to be added, because we have a feature called invisible indexes. So what we basically try to do is today we're DBAs manually. We have the ability to create indexes without actually turning them on. We can replay a certain query and do it in such a way that we can run it for, say, until we get 5% of the rows. And that's enough information for me to figure out is this index useful or not. We use techniques like bind peaking, bind graduation, which allow us to look at the various values within a SQL and predict how much the cost of the SQL is going to be without actually running the SQL itself. We have the ability to predict if a histogram is going to be useful or not. So there's a whole bunch of technology that we've always had. The interesting thing here is trying to mimic these automated actions by using this technology and using a reinforcement learning algorithm till it comes to a point where the index efficiency is the maximum. It's something we played with, it's something we have released for our customers for the previous release. But this also is a concept of the self-managing database where we write some of this stuff. We use all of these algorithms: classification, clustering, regression, associative, collaborative filtering, as well as deep neural networks. I have just maybe a couple of more slides. I wanted to go through for technologies that we use. We use a whole gamut of stuff. It's a mixture. It's a mixture of RStudio. It's a mixture of people writing stuff in notebooks, people writing stuff in Spark, because we use Spark batch engines for processing some of the log metadata entries. Some of the machine learning code is written in Python. Some of it is in R, Scala. We got all frameworks. There's a lot of Oracle products that basically provide some of these capabilities. So we use all of these. So there's not one single algorithm, one single way of writing some of this stuff. But majority of the users are basically using notebooks, Python, or SQL. That seems to be the predominant area where most of the stuff gets written. We also have connectors. These connectors can work across NoSQL, can work across object stores, can directly interact with the Oracle database, right, to Kafka queues, pull data from Hadoop, Hive, Pig, Mahout. It doesn't matter where the data is. We have the person, my stack, when we write this stuff, right, we don't have to figure out writing connectors for all of these. This basically works automatically with most of this stuff. A lot of the frameworks that are available in open source, we use all of these. And so that's why I'm just saying that there's no one way to solve this problem. And whichever algorithm, whichever combination of algorithms provides this, we use this. One thing I did want to mention, there's a lot of emphasis on in-database machine learning. And we have this option, and we've started to use it more and more for all our use cases, where we can perform ML directly inside these HTAP models. And one of the biggest reasons we use this, single, not because this is like, it's Oracle, it runs inside Oracle, that's why we have to use Oracle. That's not the reason. The single reason we use this is we don't have to move the data. One of the biggest problems we've had before is you always have to extract the data out of the system, put it somewhere, do some analysis, and put it back. There's data replication, there's movement, there's data cleansing, extraction. There's all sorts of problems that, that's 80% of the problems come with that. When you have to move things around and when you have to duplicate data, then data consistency considerations come into extent. So one of the cool things with most of our metrics is they basically sit inside an Oracle database. So for us, without having to move the data, if I can run an algorithm directly on something that actually sits in a particular data source, that's actually been an incredible help for us. There's about 30 plus different kinds of algorithms that are available inside the Oracle database. I just want to mention what all we use. These are the various varieties that are available for text mining. We use PCA for feature extraction. We use 1 and 2 class SVM. Some of these are really old algorithms, but they work pretty well for some of the use cases. But my favorite is all the time series and the anomaly detection algorithms. That's kind of my space. That's where I spend most of my time playing around. But there's also a lot of statistical distribution algorithms, which are usually more than adequate for us to doing what we want to do. Sometimes all you need is a SQL lead lag function, or you want some sort of a windowing function, or you want to just do an ANOVA test. It's all of these functions are simple calls and APIs. So it does not take us too long to build these use cases because most of the implementation for this stuff is already available for us inside the database. So that's why we kind of, if it's a choice, if the data sits outside, if it's textual, we process something on the drive directly, on the object store directly. But if the data sits inside the database, especially from a self-managing database perspective, we have a pretty decent engine that performs statistical functions using data mining, as well as has support for a whole bunch of algorithms that are present inside the system. One new thing that we added recently was AutoML. Now this is very interesting because it kind of like, there's a lot of people try to do this manually, but auto model selection, there are the four aspects, right? There's pick the attributes for the model. There is figuring out what algorithms to apply, what features to extract, and what hyperparameters to specify. And you take these four combinations and you iterate over them for every use case for as long as you can till you get actually a good value that represents something that your use case reflects. Then do an A/B test on it. That's a very standard cycle for us. Earlier, we were moving data, we were processing, and then later on we lose track and like, okay, what model was it? We try to establish something that does something similar to like an ML flow kind of a system, which has, which tracks our notebooks, which has collaborations across teams and stuff like that. Then the two last pieces of this puzzle, which is what we use. One of them is the AutoML. So we just specify this and the database goes out and finds the appropriate algorithm for it and does the entire training process in itself and just tells us that this is the model you should use. And it has I can go back and say, show me the last couple of days and the models that were selected and their corresponding A/B test results. So this is something that significantly reduced the amount of time it takes us to take a use case and go to market, where I can actually deploy this across the AIOps infrastructure. The second thing is, we've got this data science cloud infrastructure. This is fairly new. It came about, I think about 3 to 4 months ago. And what this allows us to do is it provides us a complete platform to do AutoML feature selection, evaluation. And if you want to do something open source, you can just spin up a machine, run Keras, XGBoost, Scikit-learn, TensorFlow for individual projects, and then merge this result back into the AIOps platform that we run. To conclude, AIML is here to stay for database management. It's just going to get more and more integrated into it. We seem to use a lot of it already. Many of the databases, as I can see many talks that have been done before me, a lot of stuff is already progressing in that direction. The first step for all of this stuff is basically all database diagnostics need to be in a machine ingestible format. That's not true for many of the places right now. Whether it is JSON, whether it's XML, something that can be directly consumed, has well-defined fields, and you can directly process and start training algorithms without having to do a lot of data cleansing, construction, and ETL kind of an activity. A lot of people spend time modeling. It's for us, it's just a waste of time because we've written this to automate all of this stuff. So we just basically feed something to the system, go back and discuss some other problem, come back and it's told us this is the best algorithm to use. This is the combination. These are the hyperparameters. These are the attributes. This is the dimensionality reduction that we need to have. Or this is, if you're performing a cross-fold validation, this is like it should be 2 or 4 or 10-fold cross-validation that reflects a better reflection of this data set when you're trying to identify singularities. So these are examples of where AutoML is incredibly powerful and it does all this stuff for us. It's very important to get the right data. If you don't have the right data, this is something that sounds obvious, but a lot of people don't seem to follow this. If your data is bad, your outcome is bad. It's garbage in, garbage out. But a lot of people seem to get deep into a project and you look at it and say, this data doesn't make any sense. We've found that a couple of times in our team when we're processing something, and it's extremely expensive to any kind of a data science project to find that the input data that you were training with was wrong. Models usually require a lot of data, but this one actually works really well with sparse data. Nowadays, models are getting better and better with sparse data because there's already a pre-configured set of data that's available for training the model initially. Lots of other methods like active learning, transfer learning are currently available where model training in a certain field can actually be applied to some of the other fields. Like if I've done something with CPU consumption, I can apply that to memory consumption without doing the same amount of training that I need. And of course, because there's a ton of data sets available already out there. More and more processing will move closer to the data to avoid replicas. And AIOps is about 80 to 85% automation. 15% is machine learning. And deep learning is not the answer to everything. I've seen people try to use deep learning for everything. In our case, most of our algorithms, simple classification, regression, clustering algorithms give us extremely good results. Thank you so much. I'm sorry I'm a bit over time, but I tend to lose track when I'm presenting all this stuff. I hope this was useful.
Great. Thank you so much. This definitely gives everybody a sense of how these things really work in the real world. This is fascinating. So we have, I know that we're running over now, but let's do just a couple of questions that have been submitted. The first one was, when you do hot winter algorithm forecasting method, how are you treating exogenous time series, if you take them into account at all?
It depends on the use cases. Some of the use cases we have exogenous time series, some of them we don't. In most of the use cases we don't. So we don't have to do anything different for exogenous time series as compared to what we have to.
Okay. Good. The next question has to do with instrumentation, because to do all of these things, you will need very detailed ability to do instrumentation. Can you talk a little bit about how you address this kind of issue?
There's a couple of ways that we have done this. The first thing is you have to have some kind of an in-memory tracing. So we, as for databases, we've always been pretty detailed as far as instrumentation is concerned. It's always factored in within our code for the last couple of decades. There's first is the instrumentation itself. The second thing is the place where you can utilize the performance tuning teams to run through this code and track overhead that's specific to this instrumentation. We have done this both on a periodic basis. Our instrumentation overhead is typically no more than 2%. The different kinds of instrumentation we have attempted is inline instrumentation within a particular process, which has not exactly been great as far as scaling is concerned. We now revert to something called in-memory buffers, where every process that's basically writing something out, it tends to write a certain set of functions as it processes them. Whenever an exception occurs, this in-memory buffer gets written out. So the overhead of the instrumentation is significantly lesser. Also, for every kind of instrumentation, there's a severity level associated with it. Is this trace? Is this error? Is this warning? And in addition to that, we also have the ability to say, I want either high level or medium level or low level of instrumentation tracing for every component. So there's a certain spec that every component needs to follow as far as its instrumentation is concerned. How much data can they write? There's literally a quota that each of these components can write to. If they write way more data than that, then we can rotate their log files out. We don't print out their in-memory buffers. So they lose a lot of the data in the in-memory buffers. And then the instrumentation for those certain components degrade. When we test a particular product, like before our database product goes out, we test this stuff in the lab for at least a couple of months. We have the ability to say that this component has a diagnostic score, how good this component is as far as diagnosing. And the consideration is how much log data do they produce, how easy it is to read the log data, how much amount of post-processing has to be performed for this log data, and what is the total performance overhead for this log data. These are the 4 things that we take into consideration when we are evaluating each and every one of these components. And during the process of testing of these components, we can say, oh, this component is great, this component is not so great. And then we reflect this back to the individual team, and they go back and recode some of the instrumentation to reflect the standards we want this to reflect. So the simple answer to your question is, we've had a ton of instrumentation. We have a process around it. Some developer can't just go out and say, write as much as I want and get away with it, because we have ways to catch this. We have instrumentation. When a person submits a transaction, it will automatically run a bunch of tests and track the percentage of log entries they generate. We even have code that looks for replicating log entries. If a log prints the same thing, say 40% of the time, and the same log line appears in more than 40% of the log content, we have the ability to flag that out and say this developer needs to fix this transaction, and we don't even let their transaction merge. So it's very important to develop these practices at the beginning when the developers do not insert this code into your project before it's sent out to production. And you catch this at the time the transaction is checked in. You have a process around what is an acceptable amount of instrumentation. 2% is acceptable for us, so we stick to that. Anything more than 2% gets flagged out. And we also look at how many times the defects punted between the testers and the developers. If this punt happens many times, which means the diagnostic is insufficient, and we automatically flag those components for review. So there's a whole bunch of stuff that we have done to address how our data can be rich without tanking the servers. At the same time, we have enough instrumentation, just the right amount of instrumentation to be able to go out and say, yeah, I can troubleshoot this problem.
Great. So yes, we have learned that a lot of diagnosis is actually built into the product itself. I noticed that, Rao, you mentioned merging transaction. That's an Oracle speak. It's really merging the module being developed in Oracle. Yep. We call them merging a transaction. It has nothing to do with the database transaction. So anyway, but the point really is that yes, the diagnostic is actually completely built into the product itself. So it can spill out these information for mining purposes. Next question has to do with privacy. If you're in the cloud, you have diagnostic information or tracing information coming from all clients. Are you concerned about privacy?
Absolutely concerned about privacy. So first thing is our logs do not have any client information. We just pull whatever logs that the database spits out. We have the ability to, first of all, not pick up anything that we can think that will contain any client information. We ensure, this is something you have to fix at source. You ensure that no database tables ever get dumped into the logs. You ensure no cursor information gets written into the logs. You ensure no bind variables get written into the logs. We don't have access to your data anyways. So we have access to the logs that are generated from the common infrastructure that all your stuff runs on top of. We do not use this log data to train our data sets. We don't need this log data to train our data sets. What we do is our engines run on these logs and strip out anything specific, which is IP addresses, host names. We got to do all this anyways for our cloud because it's like we don't want anybody getting their hands on this data and saying, oh, we know how to connect to this VCN, and this is how bad habits happen, right? So the first thing is we don't use this log data to train our models at all. We've had a lot of good training models internally that we can simulate customer workloads over the years. And we use that and a combination of a tool called Swing Bench to generate this workload on top of our servers. How do we get these workloads? So as a testing principle, Oracle over the last 2 decades has been collaborating with customers to give them better quality of software. We sign agreements with customers where they give us anonymized workloads of their, and we have hundreds of these. And we run these workloads to test our software anyways. And this is something we, before we put the software out, we will run these workloads. We use that data to train our models. So there's no customer data in these models at all. The inference engines run on top of the log data that basically comes from these servers, and they are all running in containers. Once the inference is derived, the result of the inference is processed, the container is destroyed, along with all the data in it. Nothing comes out of this infrastructure. If someone wants to see something, it has to be curated pretty heavily. So the two main answers to your questions is, first of all, we have no customer data in our logs. We ensure we don't print anything. The second is we do not train our models on top of any customer data. We train it using whatever models we already have internally. And if these models regress, then we go ahead and train these models based on our own internal data. So we're okay if this model is like not 100% accurate. If it's even 80%, we're great. We're super happy with this because we don't want to run anything in near real time on the customer systems, which would compromise performance. Remember, our placement factors are very dependent on this. And we want to try to pack as many people as we can into a server to get the best performance and the best bang for the buck for the customers. So how do you reduce customer costs? Do not run anything that is not customer related on the servers. Move all this processing off the customer servers and run them somewhere else. And do not do any training on the customer servers or anywhere else. All this training is done in the lab using our own data. So, and even the log data that we generate is anonymized. We have to do it as part of our security requirements.
Okay, so great. We do have a couple more questions on the chat, but I think since we're already running over quite a bit, so I'm going to then close this and have these chat questions given to Rao, and hopefully he has an opportunity to answer them offline. So at this time, I wish to thank Rao once more, and And we will, I guess, take a 15-minute break and to come back to the real afternoon session. Thank you very much. Thanks.
Thank you, guys. Sorry to eat into your lunch. I hope you guys are doing well and enjoying the rest of this conference. Thank you.
Thank you.
We hope the Oracle will treat us with a lunch.
It's a virtual one. Enjoy it. Okay, so panel, so we're coming back.
Yeah,
when?
we'll coming back in about in 15 minutes.
In 15 minutes.
And we'll go over the second session chaired by Konstantinos Kostan.
Great.
Thank you.
Thank you.
So by the way, since we're in a break, there are 2 more questions here. I think I can quickly answer them before I head off.
Sure, sure.
Okay,
Then,
okay.
I'm not so sure whether we are still recording.
I think.
Yeah, we are doing recording.
Oh, still that's great. Then your answer will be included in the recording. Great.
This is one of the best parts of having a virtual conference. Is it's like, you know, a quick snack and you can get right back. I just thought if I'm already here, I might as well answer these 2 questions. So the first thing is concerning this. Yeah, so concerning the CPU usage forecasting for a new user with no observed values, is there another process which tries to match a new user with a known user so that some kind of forecasting can be performed? Workloads can be pretty predictable. You'd be surprised. More than 70% of the workloads, especially that come into an Oracle database, are kind of, you know it when you see it. So the model works very well for even somebody that's just come in, and it's the anomalies that you need to detect in that workload that actually takes some time. So like, even if I can predict a new user 70% of the time accurately, it takes me at least a day or 2 days to look at this person's workload enough to determine a pattern that I can forecast their anomalies. But most of the anomalies for these users are predictable. So people come in, you know, they run a whole bunch of SQLs in the morning, they run a whole bunch of SQLs in the afternoon, they run a whole bunch of SQLs in the evening, and then the database backups happen at night. That's usually how most people's workloads function. If the system is accessible across the world, then there's a slightly different model. But it's very easy to apply what you've already learned in the model to an existing workload that's already there and get it right about 60 to 70% of the time. For the unusual workloads where people start doing, like, for example, all the workloads right now during this COVID timeframe is unusual because people are working at different times, people are working from different places. Somebody's stuck in a country that they're not supposed to be from, and they suddenly start accessing the thing. So that's where the models take a hit. And there is, the models are configured to be more conservative so that if they make a mistake, they can recover quickly from the mistake and go back and try to predict things accurately. If you try to make models extremely accurate, then a mistake proves very expensive because it has to go back and unlearn a whole bunch of stuff and go back and relearn something new. So it depends on how you configure the algorithms. So the algorithms are extremely sensitive to exceptions. Then they take a long time to recover. The algorithms are generic enough, and you categorize something, this is a generic workload, and you feed that in, and then you try to figure out these exceptions as you go. The model works much more efficiently. We've actually, by the way, so we are experimenting with active learning to try to transfer some of this content from an existing process that it already knows into something that is some new user that actually comes in. And we try to learn as quickly as we can based on what we already know. But again, this requires us to actually run ML on top of the current load that's actually running. There are a lot of considerations to not running ML on the machine where you're actually doing things. So we wrote a stack that is very selective on pulling specific pieces of data, and it does analysis using that data. And all the machine learning on top of this happens outside of that data. That's a very successful model to scale out. if you run ML inline in the server that you're running, even inference engines, it's stated that inference engines do not consume as much amount of resources. That's not an accurate statement. If I run an anomaly timeline piece of code, I can easily chew up 10% of a server if I'm running on a 4 CPU server. So it's you need to be careful that the problem you're trying to solve is not perpetrated by the process that you're trying to use to solve it. So you have to ensure you don't contribute to this problem. Let's see.
The last has to do with
the last one,
model deployment. Yeah.
Correct. So we have a complete CI/CD process for this. Okay, it's called MLOps, and every user that basically writes a piece of code, like let me use GitHub terms for benefits of not using merging transactions and stuff like that. So basically, you basically write a piece of code and you check it into a repository, and you have no idea what this code is going to do. This code can be a piece of a notebook. It can be a bunch of SQL that is in a notebook that's changing something. You're dropping a model. You're trying to transfer or pickle a model from one format to another format using Onyx. So there's a lot of ways this thing can work. So it's like we first of all established a complete end-to-end CI/CD process. Like how you take some code, you put it into a repository, a certain amount of tests get run on the code, it generates a Python egg file, it gets deployed out using Hudson or Jenkins, and then it runs away on runs on some servers, and then some users run on it and say, hey, this is crap, this data, it doesn't make any sense for me. And then it comes back as feedback to me saying, hey, your transaction caused a lot of problems, and this A/B test for these 4% of the users failed, and we have backed it out. And we have gone back to the old model till you can actually check in and fix this code. And this feedback is available to the user instantaneously. So we basically have a CI/CD cycle that allows us to release every couple of hours, but it's overkill. Based on our studies we have seen, usually 1 week, a deployment of 1 week is good enough because the models don't change that significantly. And so the flow is very simple. We have some code, we write into a repository. There's something that checks the code out of the repository. It runs a whole bunch of tests against it. It builds a Python egg file. It deploys it into a test environment. If it succeeds deployment and it runs and checks off the basic tests, then it goes live on a certain set of AIOps servers. Have the ability to say, okay, these 2% of the servers will basically be running AB all the time. And it pushes these off to these AIOps servers. The deployment happens. If something goes wrong, it will automatically, there's a threshold that we have defined. Like if the regress from the original is about 5 or 6% off as compared to what the previous model gave, immediately the model is rolled back, the previous code comes back into being. The customer sees, hey, something's not working. It's like, you're looking at your Facebook feed and you see irrelevant stuff, you refresh, then you don't see irrelevant stuff anymore because the model just went back to the original model that works really well. And the user basically gets a notification saying, this piece of code you wrote gave a not so great result, and this is what you need to do to fix it. So the entire end-to-end pipeline is completely isolated from the actual individual developers themselves. So the pipeline is designed to scale. The testing is designed to take this thing out of the hands of the user and to ensure code quality. The A/B testing is automated so that developers don't need to worry about if you chuck in bad code and it fails compilation or it destroys the model completely in test, it will never make it to an A/B test either. So there's so many ways of deploying a complete end-to-end CI/CD pipeline as far as machine learning is concerned. And we track every check-in, every model run over a period of time. The model runs we do, we basically generate model IDs. The model IDs for the runs that were successful, they're all stored and categorized. So I can go back and see the entire week and say the last week, these 10 models worked great for this use case. And for every use case, we have about 5,000 to 10,000 runs every day. So you can just imagine how much amount of stuff that we are playing with. Sometimes, of course, earlier we used to do many, many more runs to figure out if something is good or not. Nowadays, we don't have to do as much runs because the models have pretty much stabilized. So as the maturity grows, the amount of testing that you have to do using AutoML to find the right, so in a model deployment, the number one thing that makes or breaks things is your test and training data set proportions. If you don't have, if you're not able to isolate the anomalies within your testing and training data sets, like for example, do you run 10-fold cross validation to identify all these singularities and get rid of them? If you can figure that out for your model, the model stabilizes immediately. It's very easy to push a deployment process cycle to it. If you can't figure this out, it's a problem.
Okay, so I think we're going to have to give everybody at least 5 minutes for a bio break before the next session.
See you guys.
So really appreciate all this insights that you are sharing with us. Okay, so
thank you so much,
one
guys.
more time. Okay,
enjoy the rest of the conference.
Yeah. Thank you so much as well.
Thank you. Take care.
Bye-bye.
Bye-bye.
Okay, let's wait a couple of minutes. Let's check if the speakers are online. Parimarjan Negi, are you here?
Yes.
Okay, cool. And Zara Sadri, are you here?
Hi, yes, I am here.
Okay, cool. Okay. So hello everyone, welcome to the second research session. I want to apologize for the delay, but we had interesting and informative questions and answers, and I hope that you had a good lunch. This session consists of two talks. The first talk is titled Cost-Guided Cardinality Estimation Focus Where It Matters, from Parimarjan Negi from MIT. Parimarjan, if you want to talk about yourself and brief introduction.
Hi, I'm Pari. I'm a second-year student working on like kind of machine learning for databases type of stuff. Yeah, that's it, I think. I hope you like the talk. Thanks.
I'm Pari, and today we are going to talk about cardinality estimation. Now, cardinality estimation is a huge field in databases, and it's being used in approximate query processing or query optimization. Our focus will be on query optimization in the scenario of query feedback. So that what this would imply is that the learning agent would see a sequence of queries and it will try its best to approximate a model based on those queries, and then it would answer cardinality estimates on future queries. Now, what does a model like this look like? The pipeline would start with collecting training data, which is just a lot of queries with their true cardinalities. Then we will featurize them in some way so that it can be represented as a vector of numbers, which can be fed into a neural network model, for instance. We'll choose an architecture for the neural network. Finally, we'll choose a loss function on the cardinality estimate so that the neural network would know whether it's doing well or not, and it can use this the signal from this loss function to improve its predictions in the future. Now, what are the properties of a good loss function. So let's say you have all the cardinality estimates for a single query, which would be all its subqueries, and this is all the optimizer needs to find the plan based on these cardinality estimates. So an obvious choice in machine learning literature has been mean squared error, but this doesn't do very well for the purposes of query optimization, because small errors in base tables, for instance, can propagate and become really large after joins. To solve this issue, in the past, in the literature, the best proposed method for cardinality estimation in the context of query optimization has been Q error. This is a multiplicative error, so it takes into account that small errors can become really large after joins, and it does do much better than mean squared error for this, for the purposes of query optimization. But what we really want to optimize for are the runtimes of the queries. The runtimes that are too slow to compute during a training iterations. So instead, we defined something called the plan cost, which is a proxy for the runtimes based on the cost model's output. So let's say, given a vector of estimates, the optimizer can find the optimal plan based on that. For instance, p hat would be the best plan given the estimates y hat. And so the best possible plan for given cost model would be p star, because the optimizer was given the true cardinalities to find this plan. Now the cost of these plans can be found using the cost model and the true values of each of the subqueries. And similarly, we can define an error, which would just be how far away this cost is from the optimal cost. Now, let's go over an example just to make sure these ideas are clear. So let's say we have a query over 3 tables here with some arbitrary filters. One possible plan is to join A and B first, and then we'll assume a very simple cost model in which the cost of a join is just the size of the 2 join operands. Similarly, another plan joins A and C first, and its cost. Let's just remove the common terms from these. So our choices for which plan is better would just depend on the estimates for A join B or A join C. Now let us look at some true values. Let's say these are the true values for the given query. Then the plan A has lower cost because A join B is cheaper. So here we would choose plan A, and the cost of this would be 5. And the Q error is 1 just because these are the perfect estimates. Now let's say, let's look at an estimator which estimates both of these quantities exactly double. So the Q error now would become 2 because it's 2x off the true values, but the best plan still remains A that the optimizer would pick because A join B is cheaper under this new estimates. The cost of this plan though would not depend on the estimates, but on what the true values for each of these costs were, and so it's still 5. But let's see what happens if the cardinality estimator improves the A join C estimate and estimates that perfectly now. Q error improves, obviously, but now A join C is cheaper than A join B, so the plan that the optimizer would pick given estimate or choose estimates would be B, and it is a worse plan than what it had before with worse cardinality estimates. So this shows how minimizing for Q error might not lead to, actually might not minimize plan costs at the same time as well. And so so this begs the question, can we not directly optimize for plan cost itself? For instance, as a loss function. Unfortunately, plan cost is not differentiable, and it is crucial for the loss function to be differentiable, because otherwise the neural network would not know which way to adjust its parameters, because it depends on the gradients of the loss at each step. So instead, we propose a new way in which we use the signal from PlanCast in a different way by sampling the training sample or the training data differently. So let's look at how a typical training loop for training these models would look like. You have a lot of training queries, and you sample each of them with uniform same probability and feed them into a neural network model, which is trying to minimize skew error. And this would continue over and over again for many epochs until the model gives you reasonable performance. We'll start the same way in our prioritized training loop. And initially, all the sampling probabilities are the same, but after every iteration, we'll compute the updated costs of the plans that come out of these estimates. And based on these costs, we are going to reweigh the sampling probability for each sample in our training data set. What this would imply is that, for instance, here, the first training sample did not seem to, probably did not have a large plan cost. So we would assume that our model is already doing well enough on this, even if the Q error may have been higher. So we would see it less frequently in future training iterations. And the model will be able to focus more on something like the second training data point here, which has had higher costs. So it is sampled more frequently in each training step. Now, to evaluate this, we built our own data set, which is similar to the join order benchmark, but it's more suited to these query feedback scenarios because we have a lot more queries for each template. So the model gets a chance to see a lot of queries from the same template, but with changing filters, so it can learn a distribution over those. And this has tables, this has queries that range from having small queries having just up to 6 tables to really large queries having up to 16 tables. We use a standard training setup in which the data is split into 50% training data on which we train our models and then evaluate it on unseen data. And we use neural network architectures based on recent papers. In the results, we'll show the results from the MSCN architecture, which does slightly better on these tasks. And we use the post-quest cost model to compute plan cost, as we described earlier. So on the MSCN data, without prioritization, would be what the model was the same as the model was proposed originally, and that does a lot better when we compare the Q errors compared to the prioritized training loop that we showed. And this is expected because this model was trying to minimize Q error, and it does do that. Notice that in our prioritized training loop, we may not have seen certain samples often enough if it had low enough priorities. So it may do a lot worse on those samples here. What we care about are the plan costs. And on that, the prioritized training does seem to pay off and the model does a lot better. And more importantly, this gain seems to translate to the runtimes as well on these queries. And the counterintuitive thing here is that it does this despite having a lot worse Q error. And despite being counterintuitive, what is crucial here is to look into what kind of queries, what are the kind of queries where the one of these models is better than the other. Now, if we take the MSCN model trained without any priorities and look at the runtimes of all the test set queries, and sort them from the slowest to the fastest. And if you look at the 25% of the slowest queries on that segment, this model does a lot better on Q error. So the model is able to minimize Q error a lot better on this segment than when we trained in the prioritized setting. But if you look at the slowest, so this was the fastest 25% of the queries. So these are the queries where based on the plan cost or the runtime measures, we would probably care a bit less, because these queries, even with worse estimates, presumably can run fast enough. But if you look at the slowest 25% of the queries, these are the really important queries. On this segment of the data set, the models trained with priority do a lot better. And this is because during training, we sampled similar queries which had a high plan cost and which would have taken longer to run a lot more often for the prioritized MSCN model. And because it saw these types of queries more often, it's able to learn features more relevant to these queries. It's able to focus its model capacity on this segment, on these type of queries. And this is the kind of behavior we would ideally like for our learned model to have. Now, in conclusion, we defined a new metric, and we and a way to benchmark cardinality estimations models for these for this kind of scenario, and we proposed a way to include this signal into the standard training process of neural networks. This is just early work. There are a lot of interesting ways to push this further. For instance, can we define a better metric other than Q error that we can minimize, which may directly be related to the plan cost metric, since that's what we care about. Another thing is that all this relies on generating the true cardinalities for all our data set. This is an extremely expensive process. So can we somehow do this faster? That would make these techniques a lot more practical. Thank you.
Okay, thank you very much for the interesting presentation and talk. There are a couple of questions in the chat. The first one that you already answered is how good was the cost model on dataset? How do you handle errors in the cost model if it exists?
So the cost model that we used was just a default cost model from Postgres, and we don't handle any errors in the cost model. What we saw is that if we feed in the true cardinalities, the performance is a lot better than with any of these estimators. So we just treat the cost model as a fixed arc.
Okay, thank you. The second question was, what are the feature lists used to train the model?
The featureizations have been based on previous papers. Essentially, you specify like the join, you have a one-hot encoding for the joins and the tables. And then for predicates, for continuous predicates, you can do it based on the minimum and maximum value on the column, which is straightforward. And for discrete features, we just use the simple featureization of whether it's present or not and what the Postgres estimate for that feature would be.
Okay, thank you. There is a follow-up question. The initial example that you showed where the Q error was smaller, but the plan cost was higher, can we attribute that error because of the cost of the model?
So the plan error itself, the plan cost itself is based on the cost model. So the plan cost assumed is in the units of the cost model. It's based on the output of the cost model. So the errors in the cost model could only show up in the runtimes. And we see that in terms of runtimes, generally the trends seem to be pretty similar in the cost model and runtime outputs.
Okay, thank you again. We have another question. Did you try your approach on join order benchmark, Joe?
Yes, so Essentially, we use query templates that are similar to the join order benchmark. The join order benchmark has only about 4 queries at most in each template. In the training scenario that we had, in which you have you see half the queries, let's say in your training set and half in the test set, it is required that each template have many more queries. Otherwise, there would be no chance of generalizing to the unseen data set. So that's why we generated a much bigger data set, and we this is all published online. But we hope that it's sort of has very similar properties to the join order benchmark, but just with a lot more queries.
There is a fun question. How is it related to a chess playing game theory? Chess player, right?
Yes. Doesn't help me too much in debugging Postgres, unfortunately.
Okay. Thank you very much for the answers and the interesting talk. We can move on to the next talk, which is titled Online Index Selection Using Deep Reinforcement Learning for a Cluster Database, from Zara Sadri from University of Oklahoma. Zara, do you want to introduce yourself?
I have a short introduction in the video, but in brief, hello everyone, I'm Zahra Sadri, and I'm from the University of Oklahoma, and my research is mostly about applying machine learning or data mining approaches for index selection. And thank you for listening to my talk.
Thank you.
Hello everyone, I'm Zahra Sadri, and today I'm talking about my research, which is online index selection using deep reinforcement learning for a cluster database. The outline includes an introduction about the index selection problem, the objective of the research, and the overall picture of the proposed workload, and then I will explain all the modules in the diagram in details, and finally I conclude the presentation by open challenges and future work. The index selection problem is a task of selecting and creating a set of indexes for a workload with the aim of minimizing the processing cost of the workload. There are many index advisors, mostly for databases deployed on a single node. Our focus in this research is designing an index advisor for a cluster database. By cluster database, we mean a cluster that consists of several database engine nodes, and data is replicated among them. And you may ask, why not simply using one of the existing index advisors for a single node in a cluster database? Because we want to consider features of a cluster database, such as load balancing and fault tolerance. Throughout this research, we have some definition, including query template. By query template, we mean a representative of a group of query instances with the same format and different values. For instance, we have a query such as select whatever from table 1, where the value of the column is less than or equal 90. We consider all of the queries similar to this query in one query template, and we just simply replace the value of the parameter by a placeholder. Indexable columns are those columns that appear in a word or join clauses in query instances. The objective of this research is to design an index advisor to create index configuration on different nodes of a cluster database using deep reinforcement learning with 2 objectives. First of all, minimizing the query processing cost for the workload in the cluster database, and then decreasing the load scope. By load scope, it means that we don't want to have a different amount of load on different nodes. For instance, we don't want to have case that one node is completely idle and doing nothing while the other node is overloaded with processing all the workload in the cluster. We want to avoid these cases. And the assumption of the research is that data is fully replicated among the nodes. Now let's have a look at the overall picture of the solution. The solution consists of 5 main components, including Workload Forecaster, Pre-processing module, Deep Reinforcement Learning Framework module, and Cost Estimation and Routing modules that I'm going to explain each in details in following. The Workload Forecaster receives a workload and time interval, and it predicts the workload of a cluster database, and also it returns to us the query template and the query instances of each query template that we needed to use in other modules. The pre-processing module receives the predicted workload and query templates and extracts the characteristics of the workload by creating a workload matrix, an access vector, and an index selectivity vector that I'm going to explain them with an example. As you can see in table 1, we have 3 templates and also the number of the instances for each template. For the pre-processing modules, receives the query templates and extracts the indexable columns from the query templates and create a matrix which we call workload matrix that shows which indexable columns appears in which template. For instance, column 1 and column 2 appears in template 1, so they set to 1, and the other columns set to 0, which means that they didn't appear in the template 1. An access vector shows the total number of access to each indexable columns, and index selectivity vector shows the value of index selectivity of each column, which is calculated by dividing the number of unique values in the column divided by the total number of the records of that column or table. Okay, now let's talk about the Deep Reinforcement Learning Framework. This module consists of 2 components, agent and environment, and it formulates the index selection problem for a cluster database as a deep reinforcement learning problem, which works based on the deep reinforcement learning concept where an agent interacts with the environment, and the agent learns to select an index configuration for each replica by interacting with the cluster database, which is our environment here. And at each time step, the agent selects an action, and the environment receives that action and take that action and return the new state of the environment and the reward value to the agent. I will explain each how to calculate the reward and new state in the following. The environment is responsible for showing the new state of the environment and what are the actions that agent can take, and the reward and calculating and returning the value of the reward function, which shows the goodness of the action which is taken by the agent. To calculate the reward, the environment is interacts with 2 modules, which are routing and cost estimation, that I'm going to explain later. For showing the state of the environment, we have 2 components. First of all, it shows the current index configuration on each node in a cluster, which is shown by a state matrix. And also we show the workload characteristics of which we have already discussed this part. Now let's talk about the state matrix. Suppose that we have 2 nodes and 4 indexable columns. As you can see, in node 1, column 2 and column 4 set to 1. The reason is that it means that there are indexes on column 2 and column 4, but there is no index on column 1 or column 3. So state matrix shows whether there is an index on an indexable column on a specific node or not. Set of actions that agent can take are creating an index on a specific index column on a particular node or dropping an index. The reward function consists of 2 objectives. One of them is reducing the workload processing cost, and the other decreasing the load score that I'm going to explain each. The reward function, based on the workload processing cost, we first compute the total processing cost of the workload in a cluster based on the equation 1. And as you can see in equation 1, QAT stands for query template, R shows the replica and a node, and I shows the index configuration of a specific replica. Our assumption is that to achieve the minimum cost of processing cost of the workload, each query template should be processed by the replica that has the best index configuration for that query template. If a QAT shows the number of the instances of a template, if a U shows the number of the instances of each update, and each update applies on all the replicas to keep the consistency of the database. And the reward of the processing cost is calculated using equation 2. In order to calculate the reward for load score factor, we first compute the amount of the workload when the load is distributed among the nodes evenly using equation 3, and then we compute the workload of each replica. Then we find the ratio of the amount of load score on each node using equation 5. And finally, we calculate the reward of the load score using equation 6. And the total and final value for the reward is the weighted sum of the 2 previous reward. I mean that the reward for the cost and reward for the load score. Now let's talk about the agent. The agent learns to select index configuration for each node in a cluster database, and it is actually a neural network that predicts the Q value of each taken action using the deep Q learning algorithm, which is based on the Bellman equation. And it selects its action using the eGrid exploration and exploitation algorithm, which is a trade-off between exploration and exploitation. By exploration means that they're exploring new actions, and exploitation means that using the whatever that have already learned by doing the experiments, and it works based on the episode, which it starts each episode when there is no index on the nodes, and it stops each episode ends when the agent selects co-indexes for each node. For training the agent, we use the experiments replay memory, which is a memory that stores the experiments during the episodes and use them later for training the agent. As we explained, the environment needs to calculate the reward based on, for the cost calculation, it interact with the cost estimation module, which provides the estimated processing cost of the query instances using the Radix tool. And also it interacts with the routing module, which ranks the nodes for each template based on the estimated processing time. As you can see in table 2, for each template, it calculates the estimated processing cost on each node, and then it compares the processing cost and selects the node with the least processing cost for processing that the instances of that template. As you can see, based on the table, template 1 has the least processing cost on node 2, so node 2 will process its instances. And because the processing cost for template 2 is equal in both nodes, so the instances will be divided among these nodes. In implementing our solution, there are some challenges. First of all, the training time of the neural network, which is our agent, is very long. And also, in an assumption, we suppose that all the query instances of a template will be processed by a node which has the best index configuration, which is which if that node failed for any reason, there might be no proper node with a good index configuration to process the indexes, the instances of a template. And as a future work, we can use some approaches for pre-train the agent to reduce the training time of the agent, and also we can consider better routing strategy instead of sending all the query instances of a template to one specific node. Any question?
Okay, thank you very much for the talk. We have a couple of questions in the chat. I have a couple of questions as well. The first question was, so each node would have a specific configuration, and I want to expand a little bit about that. So you are looking on the query template, and based on the query template, you are choosing the index configuration, right?
Not only the query template, so we are looking at which columns happens in each query template, and the index selectivity of the columns, and also the the index selectivity and sorry, could you back to my presentation? Mm-hmm. So it's not just template.
Okay. So you're looking at the cost of the query in general as well, right?
Yeah.
Okay. Okay. So the second question was, if I understood correctly, the load on the node plays a role in the selection of index. Does that mean it will select the costly index configuration if node does not have much load on it?
Okay, that's very possible. So in the reward function, we consider two options as we add these two rewards together, and also we have alpha and beta. That this is user defined, and it can be kind of considered as a trade-off. That if the load balance is more important for you, you can increase the beta, and if it's more important for you to have a least cost, you can increase the alpha value. So yeah, that can be possible, but you can control it.
Okay, thank you. I have a question about the skewness. So about the load balancing. Load balancing is related with the index selection, right? Or it's only about the cost?
Load balancing is mostly about the workload that the node is responsible to process. So it's mostly based on cost.
Okay, so you are finding the queries, you calculate the cost, and then you are distributing the queries across the nodes.
Exactly.
Right? Okay.
Yeah. But we, yeah, yes.
Continue, please.
But we choose nodes based on we consider those nodes that has the better index selection for those queries to be processed.
Okay. So my last question is about the updates. If a table has more inserts, let's say, or updates, what is going to happen to the system? Are the models going to change? The cost calculation is going to change? What is going to happen?
So yeah, the model should be updated again based on the, you mean the workload changes?
Yeah.
The impact of the workload? Yeah, so the model, we have to update the model. So we consider that we have two training. First, we train the model by the estimated cost, and later when we run the real workload, so we consider the execution time and also the updates that happen to update the model, but it is the next step. I'm not working on that yet.
Okay, thank you very much for the interesting talk and the answers to the questions.
Thank you for listening to me.
We're going to have a break and then come back to the panel discussion.
Costa?
So we have 5-minute break.
I was wondering about that because Costa said we have a break, but I was wondering what was the break.
Well, according to the schedule, the panel will start at 2:20, so we still have 4 minutes away.
All right then. Oh.
So we have some
Yeah,
built-in
4 minutes.
some building time to
stretch.
To stretch a little bit. Unusually, it's been very tight this morning or this afternoon.
That's so true.
Yeah.
But all talks have been exciting and interesting, so
yeah,
it's worth the sitting in front of the screen for so much time.
I was going to ask a question to the previous speaker, ended up sending the question to you.
Why don't you ask that question? I think she's online.
If she's still online, we have 1 minute, maybe.
Yeah.
I was just wondering if I understand it correctly. You're trying to solve the problem of where to place the index. Is that correct? In a cluster? I mean, whether to construct an index and where to place them in the cluster. Or maybe she's not here anymore. That's okay.
Maybe Liz on the talk, Lee Grunwald, the second author. No, okay.
Well, I think they all are taking the break. That's
yeah,
fine.
we took the break seriously.
Yeah. But I might have understood it incorrectly as to how she was modeling the problem.
Yeah, that is my understanding. And your question is valid if they have used linear programming and how that would have be compared with the machine learning model.
Yeah, exactly. So just use some classical optimization
Exactly.
mechanism.
Okay, I think it's time for us to start the last session of our workshop. Again, my name is Panos Chrysanthis, and give me great pleasure to coordinate this panel, this business meeting on the future of TCD work group on self-managing database systems. Maybe it's appropriate for me to give some background. So basically, this was founded back in 2005. And if you read what was the objectives at that time, it's more or less whatever Herodotus started the talk, the opening session this morning. The objective was to foster research that is aimed at enabling database systems to manage themselves seamlessly, thereby reducing the cost of deployment and administration. And over the years, of course, this objective has changed its way of thinking from issues of scalability to auto admin, as well as auto deployment and all these kind of things in the new environments like the cloud with elasticity and so on. So again, back to the historical story, there was some officers that the president, the vice president, the secretary and webmaster, and the previous executive officers, committee chairs, presidents. In 2005, 2008, it was about 3 years rotation, was Gerhard Wacom from the Max Planck Institute for Informatics. Then 2007, 2010 was Anastasia Lamaki from the EPFL, followed by Guy Lohmann that he chaired their group for a year, 2 years in fact. After the 2012, Srinath Babu from Duke University was selected as the chair, myself as the vice chair. The workshop chairs at that time was Alexander Benidis and Florian. Then you can see Ashraf Abdullah was the webmaster secretary, and then a sort of counselors executive committee from the previous program committees and program chair, general chairs of SMDB. So in 2014 was the last one SMDB that was held for many reasons, and at some point May June, my co-chair, my general co-chair, and myself, and talked to Shivanath, and we said what we lost momentum, what we should do. And basically last year, after talking to the executive committee, there was a vote that we should actually give it a try to restart the workshop, and then subsequently think whether we want to reactivate the working group, the special interest group under the TCD umbrella. Last year, the SMDB 2019, it was in Macau. It seems that it was a success, so we continue with this year with, of course, the new organization. And now here we are with quite impressive participation. The opening session until also the second one, the minimum number of people were 64. It oscillated between 64 and 70, 68, 70. The keynotes, so in the morning, more than 130, or more than 80 plus in the afternoon. So it seems that there is still a great interest in the workshop itself. And the question is that what is the meaning with respect to the working group? And again, I want to bring something that a number of people said is whether the SMDB has evolved and has adjusted to the times of the current times, where now the employment of data mining and machine learning is becoming a key part of self-tuning, self-healing, and self-automating and all these things. And again, I am borrowing these slides from Herodotus opening session this morning. And this leads me actually to these questions. I don't want to prolong this. Should we reactivate the TCD workgroup with more activities? By more activities, I mean, besides the SMDB, to start a newsletter, or potentially to have a blog, and become more active and engaging with how things are evolving. Or this is actually currently covered by other activities from, the Sigmund blog or the TCD bulletin, and maybe this is a redundant activity to carry on by us. Maybe the other question is just continue SMDB workshop or coordinated by a steering committee, go away from the work group and just form a steering committee, as many of the workshops run by the previous general and program chairs with some advisory board, and possibly other options that you out there, all the panelists that you participate in this unique panel with one coordinator and 40, 38, 37 participants could contribute. So with this, I will stop, and I will open the floor for thoughts, questions. I guess in this stage, people could open their micro and contribute ideas. Don't be shy. You see, it's now you're making me feel like when I'm teaching these online classes now, and everybody's so quiet. And however, I know who is sitting behind these nice pictures. And I am tempted sometimes to call their names, and and they cannot hide as they used to do in the class by looking down. Okay, I'll pick up Guzeima. Hello?
Panos, you're putting me on the spot there.
Oh yeah, because you're my friend, so I feel comfortable to pick you on the spot.
So I mean, I think, again, these are just off the cuff remarks, but I think maybe the first thing we should think about is, are we generally satisfied with, having SMDB continue as a workshop, co-held at ICD, because I think that's the main vehicle, right, that we use to, essentially disseminate knowledge and research and whatever else for SMDB. So since that's really the flagship event, are we generally happy with that? I think maybe that's something for the people who are involved with SMDB and who are interested in being involved with it, to kind of reciprocate and say what they think.
Yeah, actually, this is a fair question. As I try, maybe I was a bit excited by the participation this year. And the question is that, can we assume that this big number of participants is a signal of great interest that around the SMDB workshop?
Yeah, I think that's really the question, right? So are we happy with SMDB being the way it is and continuing? If so, that's fine. Do people have different opinions, or we want to change anything? Anyway, that's just from my side.
Any other thoughts?
I have a small question.
Sure.
Can you elaborate more on the TCD workgroup and then goal in general?
Absolutely. So yeah, that's a very good question. So the TCD workgroup, when it was activated back in 2005, was in fact to, as we said, to promote the workshop itself. It was a hot topic. Yes, this morning Herodotus told us that the very first adaptive indexing scheme was proposed in 1976, but after 20 years, that maybe it was it didn't attracted that attention. But in 2005, people felt strongly that this should be a topic that deserve a special treatment, and the workshop started so that new ideas are brought into the forefront, also to promote and provide a bridge between the academic and the industry researchers and practitioners. So that was the big motivation. And if you see all the workshops attracted quite a number of interesting presentations that make it to a bigger papers later on, as well as keynote talks similar to the ones that we heard today from industry as well as from research labs that kept or bringing some sanity and direction to all these research activities that we are involved in. So, and the TCD, to remember the committee on data engineering, the task, it was the one that actually embraced the work group and was sponsoring it along with ICTE and later on the mobile data management as they are key venues for promoting data engineering. And as I said, the work group kept supporting the SMDB, but in 2015, there was a lab, and so this for 3 years, this was dormant. And that was now the big question is, do you activate a work group? But the work group, if it's only just to promote the SMDB, then maybe there is no need to have a work group. You can use a steering committee as many of the other workshops operate. In the event that we like this idea of a work group that is has special activities, then and like I borrowed from Sigmund, like besides the Sigmund conference, of course, and sponsoring, they have a newsletter, the Sigmund record. There is also the blog, that Sigmund blog. If we think that these activities worth of undertake in under the SMDB umbrella, self-managing database system, self-driving, and so on, then maybe it's worth of reactivating the TCD work group and notifying the TCD executive committee that this is our wish. Otherwise, we're going to leave it stay dormant and continue with SMDB again, provided that everybody feels strongly about the SMDB as a workshop meeting. Have I answered your question?
Yeah. I think I am learning a lot. Okay.
Okay.
Yes. I have some random thoughts, good and bad, so might as well share. I mean, the last few years, the general topics of machine learning and AI, of course, have been becoming more and more popular, and there's a lot of people who are trying to sort of utilize them for the sake of improving systems, either performance, availability, or system aspects. So that's definitely a relatively hot topic nowadays. So in my mind, that could be a good motivating factor for keeping the SMDB workshop. Now, of course, these topics are also starting to appear in mainstream conferences. We've seen papers of applying machine learning into systems databases in Sigmod and VLDB the last couple of years. Right, so for some people, workshops are promoting a niche area, but using machine learning to improve databases and introduce self-managing features is not really a niche area. It's also mainstream. Right, so we have to sort of think about that balance and perhaps whether we need to reorient SMDB slightly, maybe either open it up, then advertise more the use of maybe data mining and machine learning, as you said, and not only database but also large-scale data processing systems. Try to attract some other audience as well. Like I said, some random thoughts for now.
No, actually, I agree with you, because the purpose of workshops is to draw attention to a specific hot topic and promote it so that it becomes mainstream. Then in that respect, it has service purpose, because, over the years, it has actually made the self-tuning, self-managing databases a mainstream topic. At the same time, I will say that, the SMDB evolved over the years, and what you have suggested, the use nowadays of machine learning was the use of statistics or some other tools in the past in order to support this concept of self-managing databases. So the concept is here, and the question is whether it's not a matter of attracting the attention, it's a matter of whether it gives a forum for new ideas to be exploited and shared and thought and critique, as well as giving a step for graduate students, young researchers to try their own ideas before these become completely mature and being accepted possibly in the big conferences, mainstream conferences. So that is, again, many of the multifaceted purpose of workshops. And so that's why I wanted to get more ideas. So I agree with you to a great extent that it needs to be kept agile.
Now, as far as the TCD work group, well, since no one talks, might as well keep going. To me, it's all about having, volunteers essentially willing to, devote their time into, promoting a blog or putting together a newsletter. These sort of things need time. So unless we have some enthusiastic people willing to put the time and push it forward, then it will be very hard to keep the work group and have it being involved in more activities.
I completely agree with you again, and to some extent, that's why I didn't want to bring only 3 people to be the panel, and again, put some questions and everybody give 5 minutes. I just wanted this to evolve more dynamically and hopefully motivate young people to step in and say, yes, this is a good idea. And then I will ask the question, can I follow up later on and get engaged as a volunteer?
Working with a strategy, I see.
So in the past, what kind of TCDE work group activities do you think were effective, and you think that may have traction in the future?
So the SMDB activities were primarily was the workshop and also special issues. And in fact, the SMDB last year and this year, we are planning a special issue in DAT in conjunction with HardDB under the umbrella of self-managing and hardware optimizing database systems. So these were the primary activities, as well as I said, bringing young people in contact with more senior and do some mentoring activities when the workshop was in person. So there was all these other activities that was promoting networking, collaboration, and so on. So these were the primary activities that I'm aware of. I know some who has been on the executive committee for many years is online. I don't know if he can share some more information about that. Some Lightstone. Yeah, he might not. So that basically my answer.
There is a question in the chat about what about bringing in new startups based on such technology and knowing how are they doing?
That is absolutely great. That is, you know, it's part of this, actually a number of startups. If you go back and see one of the keynotes, I think back in the 2010-11 was Flink. So yeah, actually this has been the case. I don't have now access to all the workshops to show you actually that was quite interesting. Actually, this is a quite interesting question, because many of the startups that we know now as big names, actually they are founders or their group gave keynote talks or invited talks as part of SMDB. In fact, I have, there was, you know, some of the names here. Florian, for example, was EMC Green Plum at that time. Okay, Microsoft Research was heavily involved. Okay, I don't have the links. That's a good. That is a good question. Actually, we can. One of the activities. So come on, let's go back to the goodbye slide. It keeps going back. It's sending me signal. That basically the blog could have actually hosted interviews and small presentation for these startups, and initiate discussions about their activities. Good recommendation.
So panels, to start apart further after what Herodotus said, is the focus of SMDB going to continue as it is now? Or, you know, let me be provocative and say without much thought that, you know, we should change it to, I don't know, pick a name out of a hat, MLDB.
So I will say we can always, again, it's the name and the branding also plays a role. You know, I don't have any strong feeling of, you know, changing the name. There is like other workshops that actually, or conference that they remain, or they kept the original name, like MDM, which was Mobile Data Management, but actually it's quite broad to include both sensor networks and all kind of IoT pair bars and so on. So in that respect, the original name was kept, but the topics were broad. So SMDB, the way that I thought of it, it was so, I never thought that this would have been the issue with respect to the name. I thought more is to how you can actually make sure that people understand that it has a broader set of topics and is driven from the new activities that they're happening in the field.
Agreed.
So as I said, these are two dimensions. One is, does it have any meaning to have a work group, or let's focus on SMDB and improve it further under a committee or a steering committee? That is basically I guess the two choices. If we agree that the SMDB workshop should continue. I don't know, there is actually, we have 30 participants. At some point, someone told me that we can vary a straw vote here or a vote using the, with the participants, maybe how we can take a vote.
So can I ask, in the past, these counselors that were attached to the TCD for SMDB, what was their role?
I believe they had a dual role. One was acting as the steering committee for the SMDB, providing continuity, helping selecting the next general chairs, program chairs, and so on. The second thing, they were representing the SMDB as part of the TC executive committee, with all the benefits and attention of sponsorship and so on. So at this point, you know, is part of ICD, but doesn't have direct sponsorship. Let's say if we wanted to give award for the best paper award, we cannot tap into the TCD budget. We have to find the sponsor. But in the case that is under the umbrella as a TCD workgroup, potentially the workgroup would have a budget, and the budget can be used accordingly. So that is maybe the only big difference, that you have a budget and you can plan some of these activities, or offer awards, or give free, you know, sponsor registrations to students and so on.
I see.
So our student work it. Do you know how to take a vote on Zoom? Is it part of the participants that you have to enable voting?
So usually, I don't know if it's because you're sharing the screen right now, but usually when I'm hosting a meeting, there's usually an option down between like next to participants in chat that says polling, I believe. Right now, when I click participants, there is no option to say yes or no, but I guess you could do like.
This is exactly what I knew with my other, but since I'm not the main host, I'm the co-host or presenter, I don't know exactly how this works.
Yeah, I'm not sure either. You could also, I mean, the worst case, if you can't do like a, you know, all EAs, click the raise hand button and then see if you can get it reset and then all the nays or something.
Yeah, I'm Googling it right now, and it seems like the administrator has to sign into the Zoom web portal, and there's a polling option that needs to be enabled before the meeting. So I guess they didn't do that.
They didn't do that. Okay, good.
Yeah. So, but no, the idea with the reaction is not bad.
Yeah, actually, yeah, we can use the reaction button. So see what how things. Let me stop sharing so everybody. Let me see. Okay. So if you want to click the reaction button, to, you know, first of all, let's go with the second question about SMDB, whether you think that SMDB should continue and try to improve it by becoming more agile and more enrich its topics to attract more communities and so on. So let's click, you know, the button thumbs up.
Yeah. Anyone who agrees, thumbs up.
Well, just a clarification, does it mean that out of those two options you have, you're talking about
The second
voting,
one.
voting for the second one?
Yeah. Yeah, the other one is more.
Yeah. The problem is the reaction stays for a few seconds.
Yeah.
So
keep reacting. So I will say that
I counted at least 23, and we're 30.
Okay, that's good.
So I guess the answer is it's a go. SMDB should remain alive.
That's correct.
Perhaps, yeah, perhaps opening it up, change the description a little bit, you know, make it a little more hot and attractive, I guess.
We did that also this year, and you know, and I would say that you guys, the PC chairs, you did a good job in towards this direction.
And I mean, in the last 2 years, we've been getting what, 7 to 9, I guess, submitted papers, which is not bad. There's other workshops that I've seen that, you know, they get 4 or 5. So in that respect, we're not doing that bad, but we should do much better than that, I think.
That's correct. And in fact, one of the points that I wanted to make with the work group, that was the other dimension, is that you have a constant advertisement, you know, of the activities, not like the SMDB shows up. And then you have call for papers, and then somehow you develop a community that everybody is involved on all year around. And everybody says that now we have, and again, but the example that I have in mind is Big Viz, that also started with 6 papers and then it became 8. This year it got 20. And so again, but that was because of the engagement with the special issue that we tried to do, and also the community was so, and Big Viz is associated with the EDBT, by the way. And so that was again one of these ideas that if you have, whether you want to call it a work group or a steering committee, that will have this responsibility of having a website for all the SMDB workshops, and everybody could go back and see the history and all these kind of things. This will work better to attract much more papers. and more interesting discussions. Okay, so I guess since Herodotus did the count, the straw vote says 23 out of the 30 are in favor of the SMDB. The second question is whether we go with the steering committee or not, or the work group. I don't know how I want to phrase it. Let's put it in the order of that. Should we go with the work group, reactivate the work group? What was the one?
Well, let's. I don't want to take too much time, but let's talk about it for 2 more minutes.
Let's talk about it for 2 more minutes. Yes,
because, I mean, at least personally, I'm sort of like bouncing. It could be a yes answer, could be a no answer in my mind. I haven't decided yet.
Good.
So, and I think that the reason is I'm not clear with the trade-offs, and also whether more activities are a must, right? Because on one hand, yes, we could, if people are excited, yes, we can resurrect the work group and start more activities and so on and so forth and take it from there. On the other option would be just kill the work group. And another option would be to sort of keep the work group for, some of the key benefits, having a stable website. Maybe we don't go to create a blog or a newsletter, and maybe have the work group only manage, only steer SMDB, but try to at least maintain some momentum, year round.
Okay. So again, the work
Would that make sense, though?
is dormant.
Mm-hmm.
And I think is unless something happens soon, it already disappeared from the TCD website. It was removed. So the issue is, and now the TCD website was revamped. It has a new phase, whatever. So it's a matter of us to react and say, no, we want this to go back. And then we have, again, there is always the possibility to say, no, it's too late. We have already removed it from our books. Or, they would say, oh, we're great. You're great that you're back. Let's put you back on the website and get you invited into the different meetings and share the love of money with you or whatever.
Yeah, actually, another option is that probably we can discuss this offline, because I think not many people knows. Well, not every people in this meeting knows what the responsibility of the work group and what we need to do, and all kinds of the stuffs, right? So probably we can better think about it and probably discuss offline.
Sure, that is always an option. Again, one of the reasons that motivated me to bring it up this time around is because actually this occurred in 2014. There was this discussion. People, always there are young people, or people, they want to think more. And basically the offline discussion led to a dead end. And that's why, I wanted something to, at least some decision to be made, possibly a tentative, or let's say, executive committee that will push it and initiate this. Or we decide that we don't have to do it, because unless someone takes or the group of people take the responsibility of pushing it, even this offline, then this will not come up to some conclusion. So maybe one idea is the current SMDB organizers take this responsibility and we try to come in contact with all of you and try to get some consent and decide what to do with respect to work group.
Since we're all here, though, let's at least get some sort of indication.
Yeah, that was my feel also. That's why I
Yeah.
like to get these straw votes and see where it goes.
Right. So the two options are, leave it as a steering committee for the workshop. That's it. I mean, we can always just set up a website and put the past SMDBs in one place. That's the easiest thing to do. So, and then the other option is to have a formal work group behind it.
Precisely.
So I guess there's maybe people want to understand the cost and benefit of continuing with this TCD work group. You understand that there's some visibility, participating in maybe some promotion, as well as being able to have some access to some budget. These are probably the advantage. And then there will be some amount of work that needs to be done, and some of them may be something that a lot of people are very enthusiastic about. But maybe understanding what the level of involvement and investment that's needed in order for us to get some of these benefits will be useful. And I don't know whether that's what Yingjing was referring to, that we can discuss this thing a little bit more, and then we can recruit people to come in, even if we cannot completely make a decision right now. But I guess today we can at least understand whether there's sufficient interest to keep this topic alive, so that we, the other decision could be that we just decide to walk from the work group today, then there will be no follow-up. So one possibility is to do a follow-up, and if in the follow-up we find sufficient support from people who are enthusiastic about this idea, then we can definitely try to reap the benefit that way. And we can definitely, like Pano, as you said, task the committee that will organize this workshop as the avenue to make this thing, to conclude, to reach a conclusion, right?
Yeah, I just to point out about what it involves, as it usually this comes from the volunteers. So, for example, the segment block came out from 2 volunteers, and Yuli at this point is keeping it active and is involved with this. The segment record was the same story. It came out of volunteers, and it evolved with almost a committee now, chief editor and reviewers and so on. So some of these things is not that, we will say now we have a work group and we start a newsletter. I don't think so. I don't think that this is the prereq. It's something that also, as people join in, they would say, yes, we like to push these young people especially, bring it to new activities. And so that is, so how much work is, I think many of people around said, it depends on the volunteers and whether they want to put it. The only responsibility is that whoever is in the executive committee or the chair, vice chair, to appear in the TCD twice a year, whatever they are going to be called, in order to report about the activities and, and claim money or whatever that might be. So should we take a straw vote, whatever May has just suggested, and also I suggested in some respect, the current organizers to take the responsibility of coming with a more concrete proposal, as long as the prevailing feeling around the participants is, yes, it's worth of putting this time and exploring the idea of reactivating the working group.
Right. So we can do the same thing?
Yeah, the same thing. So should everybody use your reaction thumb up and keep it up and see whether this is...
Well, what are we voting for?
Whether it's worth of exploring further to keep the work group active. Because if people say no, that doesn't have, then there's no reason of moving on. And again, someone must be counting, I guess.
So, panelists, I have a quick question.
Ask the question,
is essentially this work group the same as the steering committee, more or less?
As I said, it's the steering committee plus recognition from the TCD as members of the council.
Okay.
That's, it's going to be, and basically as such, as I said, now the scheme that TCD has, each and every sponsor activity venue get some pot of money to promote their workshop, their venue, and so on. Whether this has been the case so far with Shofang, I became more aware of it when I was the ICD 2018 PC co-chair, and I participated in those activities, and I became aware of these details, that there is this budget that flows from the TCD to the sponsor under the umbrella venues, workshops, and conferences.
Okay, thanks.
All right, there was some talking during the voting. I sort of lost track.
Okay, let's do it.
Let's do it one more time. Now.
Okay, so have you count them?
I think it's definitely more than half. And I believe that for somebody probably is not online. So yeah, they did that.
Went for breakfast.
Okay, yeah, I think it has been a long day. Many people got very early in the morning, and there is evening, late in the evening their time. So I guess the resolution is the current SMDB organizers will take this responsibility of coming with some proposal, share it with everybody who participated, possibly not only the 31 people who are currently in this last session, but possibly all the people who participated earlier, more than 68, 70 people, and go from there.
Yeah, probably we can just put it on our website, and so that's where everybody can access. Is that a good idea, or?
Yeah, and also truly ping those 60, 70 participants as well. Send them an email.
Yeah.
Spam them.
Wonderful. Can you see my screen, my slides?
No, you haven't shared.
I tried to share them. Let me try to share them again.
Yeah. By the way, my internet decided to disconnect. So I've missed the voting and the decision, but based on the last part that I got, I guess it's a go. We'll investigate keeping the work group.
That's correct. And actually, you are the person who we selected to do all the work.
Yes, absolutely. Because you failed to count the vote. We were counting on you to count the vote, and then you suddenly froze.
Yeah, disappear. I know.
But at least you, June, was there to as a true co-chair to stand and replace those the team has shown. And actually, this brings me to the closing of our workshop. And I will also ask May to also give some concluding remarks. So from my side, I would like to thank our excellent program chairs, Herodotus and you, June, for setting up such an interesting program. I guess not only the papers, but also the keynotes, invited talks were quite informative and provoking in some respects. As a last comment, I would like to thank the two student helpers, Viva and Brian. And from me, I will again like to thank my co-chair, general co-chair, for putting together the proposal, and everybody else who contributed to the success of this workshop. I'm stealing Herodotus slides, so thanks for the program committee as well once more. Thank you so much.
Well, thank you. You concluded very well, and I think it's been very informative, and I really look forward to more interchange between the academicians who are deep down into researching really tricky problems, as well as practitioners who are trying to put these things into practice and uncover the real problems as we go towards these challenging times. So really, really hope that we can keep this thing up and get a lot of interchange going. And thanks for the program committee who selected excellent papers.
Okie doke. So with this, I will say I wish everybody to be safe and healthy, and let us hope that we are going to keep our stay sane in light of all these crazy times that we are living and going through. Bye-bye, and let's say until next time in 2021, we're going to have and please volunteer.
And show up. And thanks Brian and Viva, who were our student coordinators. Yeah, excellent job.
Herodotus, you, June, do you like to show, and Kostas, do you like to say also your goodbyes?
Sure, just a big thank you to everyone who participated and joined. I think it's definitely surpassed my expectations. With the participation was phenomenal, given past workshops. The program was really good. I'm very happy, and I'm glad I was part of it.
Well, I don't want to repeat everything where you have said. Well, definitely I want to thank everybody. And actually, we still have lots of work to do. Let's say we need to keep working on the work group, and let's think about where the next SMDB workshop. Yeah. Mm-hmm. Thank you.
On my turn, I want to thank everyone, the speakers, the keynote talks. I think it was a very interesting workshop, which aligns the academic work with the actual industry. So I think it's very nice to have this workshop. And thank you very much, all of you.
All right. Bye-bye, everyone.
Bye-bye.